Morning, everybody, and welcome to our Thursday morning session on Model Applications, Part 1. My name is David Heaps. I'll be standing in for James Cipriani, my colleague, who's feeling a little bit sick this morning, so he wasn't able to make the session. Discussions are 15 minutes each. For presenters, I have the timer, but seems like others have been getting up with a couple minutes before the end of the talk, so I'll do the same, like 3 minutes to go. So to get started, our first presentation, Saiful will be presenting on development of early warning systems in Bangladesh for flash floods and cyclonic storm surges to enhance climate resilience.
Good morning, thank you, and welcome to my presentation on development of early warning systems in Bangladesh for flash floods and cyclonic storm surges to enhance climate resilience. Myself and my colleagues from BUET, Tariqul Islam, Professor Bala, Anisul Haq, and Mohammad Asad Hussain is part of this study, and also Dr. Tom Hudson from NCAR also helping us with our modeling. Okay, so flash flood in Bangladesh is northeast region is experiencing every year. So if we can improve the early warning system, that will help the country. So my first part of the presentation is north side of the Bangladesh, we suffer flash flood. Also, we have suffered vigorous monsoon flood because we are part of the delta of the three big rivers, Ganges, Brahmaputra, and Meghna. It's come from India, China, Nepal, and Bhutan to Bangladesh. It's a flat delta. Most of the elevation is 0 to 5 meters. We also have experiences pluvial flood or urban flood due to extensive heavy rainfall, and also tidal flood and storm surge in the coastal region of Bangladesh. So it's a small country of 55,000 square kilometers, but we experience the different kinds of extreme flood and inundation hazard. And this is the Haur area of Bangladesh. It's very beautiful. And you can see some part 6 months it is underwater because of heavy precipitation in the Meghalaya basin. You know, the highest rainfall occurring station is Cherrapunji and Myshiram is there. So all the water actually come Bangladesh and inundated for 6 months. But also in the after monsoon retreat, you can see there is a paddy field, and during monsoon they have plenty of fish and also you see birds and other ecosystem, wetland ecosystem develop. But it dries, and then during after monsoon, post monsoon, they started actually planting boro rice on that huge area, and it's a very good area for rice cultivation. So this modeling effort actually trying to save boro crop if we can provide early warning before the flash flood event. And this is the three basin, Meghalaya, Borak, and Tripura. So sorry, heavy excess rainfall, convective cloud, and that occur in these basins, and it causes a sudden runoff, and the flash characteristics actually damage the crops. And this is, I think, 2017, the 90% crop was damaged. And our system has actually 4 components. One is the meteorological, that we get help from NCAR on rainfall forecasting and using the WRF nesting model. And then the basin modeling is a hydrological modeling. And then we apply inside Bangladesh hydrodynamic HEC-RAS, basin modeling HEC-HMS. These are 2 open source models. And then we compare water level forecasted for the next 72 hours. And these are the area where we disseminate the early warning information in the northeast region. So this is our domain. We have 3 nested domain, 27 kilometer 7, 9, and 3 kilometer. But downloading data, running model, we found 9 kilometer is more operational point of view convenient at the time. And then we are now trying to use the high resolution model. But when we started developing, we were using the 9 kilometer. So we carried out experiment on 16 sets of microphysics and cumulus scheme, and also planetary boundary layer. So this 16 combination includes lean microphysics, eta Fourier, and Godler scheme, and cumulus scheme is KF scheme, and Bates Miller Jenkin, and planetary boundary is issue university, and Miller Yamada Jenkin scheme. So with this 16 combination experiment, we compared with the IMD gridded precipitation and also TRMM precipitation. We found that microphysics scheme is eta is better, and also cumulus scheme Kane freeze, and planetary boundary layer UNC university scheme. But we did not explicitly run for many years because of some data and simulation capacity, but we think there is a future scope to improve, to find better for the pre-monsoon flash flood characteristics, which combination is better, also to try with the MPAS. And then we use that forecast to run the hydrological model for the basin. It's a very dendritic system, river network, and we developed a HMS system which has 158 sub-basin inside Bangladesh and 38 basins outside Bangladesh, because we don't have much information of the topography. And then we simulate with the hydrological model up to the Meghna, Bhairab Bazar stations. And these are the grid points where each point is like each gather stations in the modeling domain. We use Bangladesh Meteorological Department and Water Development Board data, and also IMD outside Bangladesh, Indian Meteorological Department data, and 11 rain gauge station in Bangladesh, 75 in outside. And we use calibration 2010 to 12, and 13 to 15, and after that we are testing the model. So we use some statistical indicator on Nash coefficient, R square, RMSE, and percentage bias to see how model is performing. But there is not much data. This is very remote area, some area. So we use the rating curve and try to capture the pattern. But you see sometimes the observation black dot miss the peak actually flat. So, but it's still we get R square 0.8, Nash coefficient is 0.92, some bias is around 11% in some cases. So we did apply the model for the whole region, the Northeast region, and then we apply the HECRAS model, because inside Bangladesh, we have the cross section of the rivers and to forecast the water level from discharge. So we have 400 cross sections inside Bangladesh, and this model performs is better, and we are now planning to apply the machine learning for that reason. And this is a Delfuse interface that is open source based interface that can apply for the flash flood forecasting for operational purpose. So this is also open source tools by Deltaras. And this is one paper we published with the season of 2021, how the open source based system is working. And we are also trying to apply two-dimensionally, because especially if they know the horizon, that what is the when and flood will be inundated. So this is under development using HECRAS 2D. So flood inundation modeling, we are currently doing for the region. So I think due to time I skip, but there's the animation on that. Okay, and then the next part is in the coastal region. We have a storm surge issues, and severe cyclonic storm actually occur almost every year. recently we are seeing the cyclones occurring. This is the last year cyclone Mosha in the formed and coming to the near Bangladesh and near Myanmar. And also this year we saw another cyclone Rimel hit Bangladesh coast. So there are several cyclones in recent times, including super cyclone Amphan in 2020, and it caused fatality is now less because of volunteer program of cyclone predictions. The coastal volunteers work, but damage is still high. So we apply 12 cyclone in the Del 3D model. We use the boundary condition from, this is the known tracks. So this is UK Met Office, Headley Center. They are simulating Ensemble modeling for 9 Ensemble for each cyclone using the unified model of Headley Center. And that data, we try to see which capture our path. So out of 9, we sometimes take 1 or 2, which is resemble the closest to the observational path. And that we run the Del 3D model in Bangladesh, which is coastal area of Bay of Bengal and some coastal region in Bangladesh. And this is also open source. We have some observational data from Waterboard and PIWT, and you see the we can see the changes of the inundation pattern during the cyclone. It's not the same for the different ensembles. So we used Joint Typhoon Watch Center data track, and also the one of 2 of the ensemble members of Headley Center. And then later we also simulate this for the climatology, like with sea level rise condition, and try to develop an inundation depth damage curve, which is important for the risk assessment. I'll show you, we developed element at risk of like how much a road or different types of infrastructure can be damaged with the depth damage curve. And we provide these cases under WSIS hub. In this, you can find the case studies of Bangladesh with environmental data tool and services. So that's it. And we are now planning to do more.
Leave room for a few questions. Anybody has some?
Thanks for the talk, Saiful. In your experimentation around with different parameterization schemes, have you tried any with aerosol aware schemes? Just knowing that that whole region, there's a lot of aerosols in the air, and yeah, how do you think that that might impact the precipitation forecasting and then in turn feeding into the flood forecasting?
Thank you, Jared. This is very important. We have not tried actually, but there is further meteorological side. We need further improvement actually to predict correctly. We found even compared to GFS and ECMWF is slightly better to capturing the flash flood event, but we can certainly do the future possibility to improving our forecast, particularly heavy rainfall forecast.
Anybody else? Okay, thank you. Our next presentation will be evaluating the use of lightning data assimilation in WRF to improve the simulation of parameterized deep convection.
All right, good morning, everyone. My name is Nick Heath, and I'm going to be discussing lightning data assimilation to improve parameterized deep convection. This is really the work of Djougou, who's a graduate student at Florida State University. So I just get to present all of her good work here. So to begin, we all know that deep convection is a challenge in WRF. And even when we look retrospectively at past events, it's really hard to get convection in the right place at the right time. And this is especially true if we're using convective parameterizations. And so this misplaced convection can lead to changes in the temperature, relative humidity, and winds throughout the whole column. It can, of course, impact the surface radiation and the surface heat budget. This can change the PBL heights and the wind direction and speed near the surface, which can impact pollutant concentrations, and then also the transport of pollution to the upper troposphere. And then, of course, it can impact wet deposition if you have rain in the wrong place. So all of this basically negatively impacts air quality, weather, and climate modeling. So back when I was a postdoc at the EPA working with John Plime, we came up with a simple approach to try to fix this in retrospective simulation. So it's a basic idea of look in a grid box in a specified time period, and if lightning is observed, force the convective parameterization to turn on using moisture and temperature perturbations. And this was applied in Kane-Fritsch. And then if not, if there isn't any lightning, you can still allow the shallow portion of the scheme to run. So we know in nature that clouds can form and even precipitate without lightning. So this was just an attempt to try to match that to allow clouds to still form even if lightning isn't there. So in practice, this just basically means that if, let's see, if there's a lightning, we get the deep convection that's going to put rain into the rain C variable. And then if not, it basically puts everything to the grid scale. And it may just evaporate, or there might be more grid scale rainfall due to the shallow convection. So this was the first attempt at running it. This was a long time ago. This is a control run on the left, just the basic Kane-Fritsch. And then on the right is the accompanying stage 4 observations for a 6-hour time slot in the summer. And so when we ran the lightning assimilation, you could see the difference. And hopefully I can just go back and forth a few times. So you could see like up near the Great Lakes region where I have that red circle, it got rid of a lot of that spurious convection that Kane-Fritsch was producing. And then over the entire eastern half of the country, you see a lot of improvements in the more localized heavy rainfall and getting rid of a lot of that spurious rainfall. Of course, right, this is cherry picked. I picked a good time step, but we've done lots of statistical analysis and it generally seems to improve things. There's of course a few cases where it doesn't work very well, but in general, it seems to improve things from a statistical standpoint. So it's been used in long-term air quality simulations, Haboob dust storms, hemispheric simulations, and several others. But a few things we were missing is a more case study approach to see how does this respond to different convective types, such as a supercell and an MCS, which is what this current study is addressing. And then another big one is how it impacts cloud top heights. So if we start looking at coupling this to convective transport, we need to get the cloud tops reasonably accurate to get transport to the upper troposphere. And then that gets to that third point of what this study is addressing is connecting it to vertical transport of trace gases within WRF Chem. So these were the two cases that Djougou studied, a supercell and an MCS that occurred during the DC3 field campaign. Yeah, we'll talk too much about these. There's lots of papers on these and they're very well studied, which is why we chose them so that we could compare our output to previous studies. So the supercell was in May of 2012 and then the MCS was in June of 2012. Here was the meteorological and chemistry setup. I'm going to focus just on the meteorological outputs, but this was run using WRF Chem so that we could also do the chemical transport. I'll also note that the comparison I'm going to show you is actually Kane-Fritsch with lightning assimilation versus the newer KF Cup scheme out of PNNL. This is just because as I've ran this in others, you get some pushback sometimes that just comparing it to the standard Kane-Fritsch, you should use a better convective parameterization to compare it to. And so we found that the KF Cup scheme did pretty well for these cases. So we wanted to give it basically a harder competitor. The lightning data came from the Earth networks, by the way. So here is for the supercell case. This is on the left is that no lightning data assimilation using KF Cup. On the right is the accompanying stage 4 observations. Here I'll do the same thing where you can see what happens when we turn on that lightning assimilation. Just kind of go back and forth. So same general trend where it improves the location generally. But here you can see heavier rainfall than what is observed in the observations. For the MCS, we see a little bit more dramatic differences. You can see, if I can get this to, sorry. the convection's offset to the northwest compared to the observations. When you run the lightning assimilation, you get much better spatial match, but again, the intensities of the precipitation don't look quite as accurate. Doing some basic grid-based statistics in MET, we found that the lightning data assimilation improved the correlation coefficient, going from about 0.2-ish to 0.4, reducing the mean absolute error and slightly reducing the root mean squared error. For the MCS case, same thing. And as you would expect, you see a much higher improvement in the correlation coefficient just because it was so far offset to the northwest. Reduction in mean absolute error and a reduction in root mean squared error. So the next thing is looking at the cloud top heights. So these are coming from GOES. This on the left is that control run, the middle is the lightning, and then the right is the observations. So again, you can see it improves the location of the cloud top heights, but we see slightly higher cloud top heights in the lightning data assimilation over a larger region, especially in the northern border of Texas there. Looking at the MCS case, again, improvement in the structure of the storm and where the higher cloud tops are. But in this case, we see that the observations have a lot higher cloud top heights extending above 14 kilometers over a broader region, whereas the lightning data assimilation only has a smaller portion like that. But then outside of it, you can see larger cloud tops over a more extended area. So to analyze this a little farther, Djougou ran the mode analysis, the object-oriented analysis in MET. And so in the top right, you can see the objects that were identified by the setting she chose for both the non-LDA, the LDA, and the stage 4. I'm just showing the results with the OBS and the LDA because that's kind of what we were focusing on, how we saw it looked better and matched some of the grid-based statistics, but what happens when we look at these individual cells? And so what we found is that the lightning data assimilation generally overproduced rainfall in these individual cells, and of course overproduced, or had higher cloud top heights, which are going to be associated there for each of the individual cells. So if you look here, blue matches the blue, the green, and the green, and so on. So that was important for us to see that in this one case, the supercell, we're getting too much rainfall and too high of cloud tops. And then in the MCS, we got the exact opposite. So the lightning data assimilation generally had lower cloud top heights. So if you look here, lower cloud than the observations, and then had slightly less precipitation. But you can see it did pretty good with the distribution here comparing to the observations. I'll note too that the non-LDA case was too far displaced and too scattered to even really compare this on the same scale using this mode analysis. So, so basically, to summarize, this LDA was used to study a case study in this case, or a couple case studies, a supercell and an MCS. It meaningfully improved the kind of the eyeball test and the grid-based statistics. And then we did discover, though, that when we look at individual cells for the supercell, it was creating higher rainfall and higher cloud top heights. And then for the MCS, it was the opposite. And so where this research is going and what Djougou's done with it is we've connected it to convective transport. I say future work, she's done a lot of this, but basically to see now how does this impact chemistry in MorphChem during these same case studies. So just to give an example, this was on the left, the lightning data assimilation. Oops, if I could do this correctly. The lightning data assimilation, this is carbon monoxide, and then these little dots are aircraft observations at about 12 kilometers. And so you can just see that when you run with the lightning data assimilation hooked up to the chemical transport, you get a lot more pollution getting up into the upper troposphere. And so this is where this is going to analyze this aspect of it. And if any of you are aware, in WRF-Chem, there's really only one approach to doing convective transport. That's the GREL scheme. And so this gives us another option for doing convective transport. It doesn't have the chemistry yet or the wet scavenging, but at least the transport of trace gases. So with that, that's all I have, and I'm excited to take any questions.
Hey, do you differentiate between IC and CG, or is it just total lightning?
Just total lightning. Yeah, it's a real simplistic yes or no. If there's any lightning in the grid box within about, we do like a 20-minute time frame. And so we actually look into the future to see if any lightning's going to occur, because then we can trigger the convective parameterization early to try to match the fact that lightning would generally occur in the mature phase of the life cycle. But yeah, just any lightning.
Do you have a hunch on whether the IC-CG ratio might help with improving the result or not?
In this case, I'm not sure. I don't think so, because all we're doing is we're using it to turn on the convective parameterization. We're not relating it in any other way. So it's kind of just like a proxy to try to force the deep convection inside of Kane-Fritsch rather than modifying the explicit variables themselves. So I'm not sure. Probably not, but maybe.
Online question. Impressive work. The question is there any chance to reproduce your work and use it in WRF as a module?
Yes, definitely. So John, I don't know if you have the code online anywhere, the lightning data simulation. If not, they can email me and we can get them the latest version. We haven't submitted it to WRF yet, mainly because it's my bad coding and there's probably some go-to statements they don't like. But we can get them the latest version, no problem, if they just send an email.
Great. Thank you so much. Our next presentation will be high-resolution numerical simulations of tropical convection for the NASA INCUS mission.
Good morning, everyone. So today I will be talking about, high-resolution numerical simulations of tropical convection. These simulations are being conducted in support of the NASA INCUS satellite mission. I'm IT Singh, a postdoc at CSU, and that is Jenny Bukowski, me. Okay. The overarching goal of the INCUS satellite mission is to understand when, where, and why only some storms, tropical storms, produce extreme weather. The key variable to understanding this question will be convective mass flux. There are four main science objectives of the INCUS satellite mission. Number one, what environmental properties control CMF? Number two, how does CMF relate to anvils or high clouds? Number three, what's the relationship between CMF and the type and intensity of weather produced? And number four, all these relationships that number 1, 2, and 3 that we will observe using INCUS data, how do they hold in weather and climate models? So before we move further, I'll just quickly mention the big wigs of the project. It's the PI is Sue Vandenhever, my supervisor. Deputy PI is Ziad Haddad at JPL, and the other two are also at JPL. Okay, so it is a tiny constellation of 3 satellites, each one containing cross-track scanning Ka-band radar. The idea here is that you have one spacecraft passing over an updraft and taking a profile of reflectivity, and 30 seconds later, you have another spacecraft taking another measurement of reflectivity, and then 90 seconds after the second one, you have another Z profile for that updraft. And the concept is that the delta Z, or the difference in reflectivity, contains information about the convective mass flux or vertical velocity here. The 30-second delta T profile, delta Z profile, will give us information about the strongest updrafts. And on the other end of the spectrum, the 120-second time-separated delta Z will provide us the relatively weaker updrafts. Also, the middle spacecraft would also carry a millimeter wave radiometer. And that radiometer would help us put this core, this particular core that we're observing with the radars into a larger context. Okay, so this is how the whole pipeline works. We are conducting some high-resolution numerical simulations of tropical convection. These simulations span all types of convective modes, MCSs, hurricanes, isolated scattered convection throughout the tropics. And these are case studies. And once we are done with them, we track the updrafts using TOBAC, which is a Python software, tracking software. Once those updrafts are tracked, we convert the model vertical velocities and condensate fields into what INCUS would observe. So K-band simulated reflectivity and microwave brightness temperatures. And those will be then fed into some sort of machine learning algorithm to ultimately get this mapping of delta Z to CMF. So here's an example right here. So you see this. Okay, so this is the model vertical velocity, and this is the model condensate field. This is then converted using a forward model into what INCUS would see, this K-band reflectivity at INCUS footprint. And then we will get the delta Z, the time-separated delta Z from this, and then map that back to the vertical velocity right here. So today I will mostly be talking about these numerical simulations that we're conducting. So this map shows the domains for all the simulations that we are conducted, have conducted, or will be conducting. Overall, we'll have more than 40 case studies. So the approach here is that we're trying to simulate cases for which we have field campaign observations. And for areas such as Congo, right here, where we don't really have any observations, ground observations, we should at least have something. So we have a GPM overpass for this case study. At least we'll get some idea of whether we're in the ballpark or not. Okay, so going further into domains and the physics, we're using two models for every case study, RAMS and WRF. And with WRF, we're using two microphysics schemes, Morrison and Thomson aerosol aware. We are using 3 nested grids, 1.6 kilometer grid spacing for the outermost one and 100 meters for the innermost one. The innermost grid will be the one that we'll ultimately use for building this retrieval algorithm. So we have quite a few vertical levels, 230 vertical levels. This is sort of related to the INCUS, the satellite vertical resolution, which will be about 250 meters. We're using same physics for all these case studies. We need quite a bit of storage for all this model data. And we're also developing a model statistics package in Python to quickly and efficiently analyze and look at all this output in a model agnostic way. So here's an animation. The shaded field here is total integrated condensate. And this is from one of our simulations over Darwin, Australia. So this was 2006. This is from the TWP ice field campaign. What's shown here is the outermost grid, and in yellow contours is 2 meters per second vertical velocity at 5 kilometers above ground level, and pink contours are 10 meters per second. So here's grid 2. And then this is what we're after, the grid 3. I'll show a few animations to just so that you get a sense of the wide variety of modes and geographies that we're simulating. So this is scattered convection. On the left-hand side is WRF Morrison. On the right-hand side is RAMS, scattered convection over Congo. This is a case study we're simulating. This is from the Tracer Field campaign, 15 September 2022. Left is WRF Morrison. To the right is the RAMS model. And this is largely scattered convection over the Western Pacific. This is from the Piston Field campaign. All these are grid 1s, so 1.6 kilometers. Leftmost is WRF Morrison, middle panel is WRF Thomson aerosol aware, and the rightmost panel is RAMs. So there are a couple of things to note here. I'm not shown here. We're validating some of these simulations with, as I said, field campaign data. There are two primary modes where the way we're validating them. Number one is we are comparing the simulated IR brightness temperatures and in some case microwave brightness temperatures with satellite data. Number two is simulated reflectivity. We're comparing simulated reflectivity to ground-based reflectivity, wherever we have those. And in some cases, it has led to quite a bit of learning for us. And the idea behind using multiple models is to get a good sample to build our algorithm. And here, I just want you to focus on this, the top two panels here. So these are just mean profiles of vertical velocities through the updrafts. So this is for an organized convection case in Argentina. And this is for the scattered Congo case that we just saw. So these are the three lines correspond to the three models. Black one is RAMS, dark one is WRF-Thomson aerosol aware, and the light one is WRF-Morrison. So yeah, we're still analyzing these simulations. It's going to be hard to trace given that, you know, it'll maybe be easier between the two WRF runs, but it'll definitely be harder to trace what's causing these differences between RAMS and WRF because the models are just very different. But the point is that we want this variety of response. We want a variety in our mapping of delta of reflectivity to CMF when we build this algorithm. The next step is after we're done with cloud model simulations, and the simulations are still going on. In fact, some of these animations just finished last week. The next step would be tracking the updrafts in these simulations. We're using this software, pretty neat, Tobac. We're tracking these vertical velocity features. Right here, you see this is a plan view through the thermal, and this is the zonal and meridional cross sections as they are being tracked. I won't go into the detail, but the whole idea is that as a thermal is moving, it's being tracked, its entire life cycle is separated into 2-minute chunks or 1/22nd chunks, and then those chunks will be used as input into the retrieval algorithm. And if you recall, the maximum delta T between the two satellites is 120 seconds. So you have one pass over an updraft, and then you have another one over the updraft separated by 120 seconds. So overall, for one model, we have about 500,000 of these non-overlapping 2-minute periods of updrafts. So we expect to have quite a few of these draining updrafts. So while the main purpose of these simulations is to build the retrieval algorithm, now that we have these simulations, quite a lot of interesting science is being done. So I am working on quantifying the length scales of variability in tropical convective environments. So the idea is that some of these products, once INCUS starts flying and starts producing data, they would be storm-centric. So you have a storm object and associated convective mass flux, associated ice water path that we'll get from the microwave radiometer, associated some sort of IR brightness temperature that we may get from some auxiliary source GOES or something, and perhaps even an associated environment from ERA5. So one of the problems that comes is how far do you have to go from the storm to get its environment? So I'm sort of working on that problem. How far do we need to go from one particular point in a tropical convective environment so things start changing appreciably? So in other words, correlation lengths of different variables. Jenny Bukowski is working on the relationship between convective mass flux and anvil properties, and other people are working on their other dream projects or whatever it is they want. So I will skip over this, some of the variogram stuff that I'm doing, and move to the summary. So in short, we're producing a very extensive database of high resolution simulations of tropical convection using WRF and RAMS models. The goal is to use these simulations as an input. It's not directly going into the algorithm, but we're tracking these updrafts. These updrafts are then being modeled we're using a forward model to produce what INCUS will see to get these delta Z's and corresponding vertical velocities. These mappings will then go into building the algorithm. And running 100-meter grid spacing models with WRF and even with RAMs is quite challenging. So for most of these inner domains, we have 2000 by 2000 by 230 grid points. And it's been a little challenging, but I think we're moving forward now. We're comparing the model output with available radar data and infrared, and in some cases, microwave brightness temperatures. We're developing a Python module to analyze this across the models, and lots of exciting science with these simulations. If you have any questions, please talk to me or Jenny. Thank you.
Yeah, great, very interesting work. So for your ongoing project, you were talking about like saying how far you need to go to actually have the background environment. But then you could look at the other way, how much data you really have in the tropics. What about we don't really have any data? So you could say from these runs how far you need to go, but what if you actually need to go a lot farther, or you have much coarser data to define the environment than what you'd like to have?
Yeah. So I'm working entirely with simulated data here. These 100-meter grid spacing simulations.
So not really worrying about it from the other way yet.
I'm not
Okay.
for now. Yeah.
Thank you so much. All right, next presentation will be on operational wharf ensemble updates at the U.S. Air Force's 16th Weather Squadron.
Good morning, everyone. I'm Berkeley Gallo. I am with the 16th Weather Squadron. Before I get started here, I want to acknowledge that all of this is definitely a group effort. We have a couple other folks here in person. So Evan Kuchera and Matt Vaughn are also here in person. So if there's anything that I talk about today, because it will be relatively high-level overview that you'd like to discuss more, please come find any of us. We're a relatively friendly group and like to talk. So I'm going to talk to you all today about some of the work that we've been doing at the 16th on behalf of the Air Force Weather Enterprise. Before I get started, though, I do want to give a little bit of an overview of what the 16th Weather Squadron does, because it's not always known. And what we do is we automate environmental information insights for national security decision advantage. So across the world, we have all of these folks out trying to complete different missions, and we have assets everywhere. So we also are interested in resource protection. And people need to know weather information. Weather is obviously a very big factor whenever you're considering aircraft. But also in terms of resource protection, there was a huge hailstorm that popped up 2 days ago over Omaha and around Offutt Air Force Base. So those are the kinds of things that we want to be able to provide this weather information from the modeling framework to be able to give people so that they can make the best decisions possible. And what this results in with the modeling side is about 200 terabytes of data and 200 million products that we're providing to 20,000 users annually across the world. We're also an operational center, and so we have to be very responsive with our data. And whether that is adapting things to move our model domains into new places quickly, or even creating new products that our stakeholders tell us, hey, we have a need for something, and maybe the model doesn't produce it. So our group will get together and put our heads together and figure out how we are going to create that information and get it to folks as quickly as possible so that they can do what they need to do. And so we utilize a lot of different models and information to do this. Our global scale, we use a flavor of the unified model from the Met Office. But on our regional scales, we are in the WRF world, and then we're evolving towards the MPAS world. We also work jointly with NASA for the Land Information System model that we use. And then from a framework perspective, we are utilizing we're starting to expand into cloud efforts, and we use GitLab for version control. So really, it's a lot of different things that we are all bringing together within our group to use. to try to be that expertise base for the entire Air Force weather enterprise. And so here are some more specific weather pieces of our mission. We have global land surface and atmospheric analysis and forecasts out to 16 days. For the regional side of things, which is what I'll be talking about a little bit more, we have fine scale ensembles at 1 kilometer and 4 kilometer, and we have different post-processing that we use to really tailor down the products for our end users. And an example of one of those is shown here. We also have rapidly updating global cloud analysis and forecasts. And this has recently undergone a revamp, and we're working on modernizing this and making it as good as it possibly can be with some state of the science things. And then also a piece that we have to consider is the cybersecurity piece. And so we are, leaders in ensuring that what we're doing is not just scientifically good, but also remains cyber secure as well. So I'm going to be talking today about our ensemble side of things, which we collectively refer to as AFWEPs. We have a couple different ensembles within AFWEPs. Our global ensemble, we utilize members from other agencies and then post-process them. But what I'll be mostly focusing on, as this is the WRF MPAS workshop, is our WRF ensemble, which is a 12 times a day, 16-member ensemble that utilizes time lagging. So essentially, we're running a member every 2 hours, but we're also introducing variety with unique physics conditions and then global background combinations. So really a lot of different ways that we are putting diversity into our ensemble. And we post-process those all together, and we're able to get these updated products out to our users every 2 hours. And as I mentioned before, we can move these domains very quickly as needs arise. So when things happen in the world, we are able to get information at those locations. And so you can see a few examples here on the right of different products that we create. A lot of them will look pretty familiar. It's probabilistic products, paintball products. But at the top, that might be one that's a little bit less familiar to this community. That is known as the Point Ensemble Probabilities product, or the PEP. And that is at one single point, you can get a essentially go, no go for these different weather hazards that are going down the chart, and then time as it goes across. So it lets you see when good weather windows are or bad weather windows are. And then inside the squares that you absolutely cannot read are the actual probability values. So even if a user has a different probabilistic threshold in mind, they're able to pull that information from this product. What we've been doing lately, we have a project. We wanted to update our core WRF version. We were at v3.8, and we wanted to update it to WRF v4.5.2. And we took this as an opportunity to really overhaul and examine the choices that were made for ensemble configuration. So yes, we're introducing all of this different diversity, but are we introducing the right diversity? Are we getting the right physics in? What have our choices been, and can we make better choices with advanced science? So I set up this 3-gate strategy for us to go through. The first is mostly a philosophical gate where, does this configuration make sense scientifically, or was this parameterization designed for a climate model and therefore not really something that suits our needs? Where the team is at right now is focused on the technical gate for making sure the configuration runs, is stable. We're an operational unit. We've got to make sure our data is getting out. Does it take a sufficient amount of time that we can get data out quickly? And are we getting any noise? And so the Excel sheet that you see there is a sheet that we do for each of the runs. We answer various questions about the technical capabilities of these combinations. The final gate is what I think of as the scientific gate, and that's where we're going to be looking and seeing if the configurations are providing improvement for different hazards and different phenomena as we go forward. The first thing that we looked at was increasing our vertical resolution. It was a relatively constrained use case instead of diving into all of the physics suites. And we know that our current number of vertical levels is below advised best practices. So we started out increasing our number of vertical levels to be in line with the HER. We did some literature review, saw that a few papers found diminishing returns for more than 60 levels. And so we were like, okay, we're going to follow the HER's example. We did have to adjust our low-level ADA levels a little bit. We increased the topmost ADA level, so there was a little bit of tuning that went into that. But we found that subjectively, we were getting improved forecast reflectivity coverage relative to observations, and just it seemed like things were going well, because during this technical gate, we also look at the output subjectively to make sure that things aren't going off the rails, as it were, because we don't want to pass something on to the scientific gate that we know is not going to perform very well. And so what we're doing now is we're just spinning up the scientific gate on these cases and utilizing MET. We have a flavor of MET that we call the Model Verification Toolkit, or MVTK. And this is going to be a test case for that MVTK to see what we are actually gaining from increasing these vertical levels. So while one group of folks is working on that, the rest of the team has moved on to testing the technical feasibility of different physics adjustments. To do this, we selected 2 baselines with those increased vertical levels, and we're holding the different schemes steady for those baselines, but varying one thing at a time. So like we'll hold all of the physics steady, but change the PBL scheme, for example, and that's what's shown here. And so on the right, you can see for the MYNN, MYJ, and YSU, we're getting things that look feasible. This is kind of a subjective first look that we do where we say, okay, storms are there, they're in roughly the right place, roughly the right coverage, things look good, we can pass this on for statistical analysis. The large image shows an example of what would flag our scientists, where we're seeing a lot of coverage, a lot of reflectivity. And so this is something where we say, you know what, I think we're going to eliminate this scheme from contention and move along to testing a different scheme. And so all of this has been deterministic thus far, testing individual members. And that in part, that's because we do run the individual members and then time lag them together. But we are going to be looking at our ensemble configuration strategy as well. So if we have a set of members whose performance we like, what is the best way to combine them? I think we'll keep that element of time lagging for sure, because that works well for us for a variety of reasons. But can we expand upon it? We have a lot of computing horsepower relative to when our ensembles were first developed. So, you know, can we improve things anywhere? And we've narrowed our schemes, but there's still a lot of combinations. So the first gate took us from 10 radiation schemes to 4. The second gate took us from 4 radiation schemes to 3. Maybe the third gate will eliminate a couple more radiation schemes, but realistically, when you think about all the different types of physics that can go into WRF, I think we're still going to end up with a lot of different combinations. So we'll probably have some tough choices to make. And for this, we're going to be evolving the MVTK verification framework into a probabilistic, to be able to handle probabilistic verification as well. So I think we'll try a variety of different combinations and see what we're getting, because the ensemble framework is very important. Like, this is how we do our high resolution modeling. It's all from the ensemble perspective. And so this is also all along the 4 kilometer, or with our 4 kilometer ensemble. For our high resolution, we run a 1 kilometer ensemble as well, and then a coarser 20 kilometer resolution. So what we find that works, we're focusing in on 4 kilometer because we had to start somewhere, but we want to make sure that when we do look at our other grid spacings, that we are not going to be breaking things, and that we will still be getting good results out of those ensembles as well. So that's what we have been doing in terms of our WRF efforts and our WRF suite upgrades. I also wanted to touch a little bit on some of the future work and additional efforts that are going on. We have started working on on-demand in the cloud WRF, and this is led by an additional flight, which is kind of like a branch in our squadron, that is called WXS, and they are really our primary technical software development arm. So while my group does a lot of the science and looking at the meteorology side of things, the WXS flight are innovators in the software development side of things. And so they have put together this rapid deployment platform to get WRF in the cloud on demand. And we've been going back and forth with them, being able to tell them some of the things that we're finding for our upgrades, saying, yeah, try, this physics combination. These would be the best ones for what you guys are using as your test case. And so we're able to integrate those latest scientific advances with these in the cloud efforts as well. And a really large benefit of this is that we can maintain our capabilities in contingent scenarios. There is nothing the military likes more than a backup plan. And so developing backup plan upon backup plan, this is something that is working extremely well as a backup plan. And there will be continued development in this area that will enable more sophisticated model setups and then also potentially higher enclave capabilities. And then this is my last slide here that touches a little bit on our MPAS efforts. So our long-term goal is to really get into this world of rapid refresh modeling, and particularly outside of CONUS data assimilation capabilities. And so being able to have a rapid refresh model that can provide information very quickly to our users with varying amounts of data that we are assimilating is something that we're working towards. And we are planning on leveraging the JEDI framework for that data assimilation. We are also getting into our MPAS development efforts quite a bit more. We've gotten some things off of our priority list, so this is rising up in our priority list. Sam Baker is leading these efforts for the 16th, and she has run part of our team through a running MPAS on our systems. And so we've gotten some of the team versed, but she's going to repeat that so that our entire team can get versed in how to run MPAS on our system. And I think that will really open up the capabilities for innovation. It will allow our scientists to brainstorm and have these ideas and be able to test them out within the MPAS framework. As we've seen this week, MPAS is still relatively young. There's a lot to be learned and leveraged scientifically and technically. And I want us to, when we learn something, to be able to share it back to the community and really engage in this community effort. We've done some testing of MPAS on the cloud as well, but really I'm anticipating this large surge in MPAS work in the next 6 months as more and more of our team gets going on it. So touching back to our WRF-based ensemble, the WRF-based MEPS, is this the last iteration of our WRF-based MEPS? Will we have, an MPAS-based MEPS in the future? I think that's to be determined, but from what I have seen here this week, I'm really optimistic about it, and yeah, very excited to be in this world. So happy to answer any questions you all might have, and like I said, feel free to find any of us at the 16th in a coffee break or later today. Thank you.
Great talk. So considering the Air Force's needs and the military more generally to have rapidly changing domains of interest potentially, and with MPAS being slower to generate new grids, I guess, have you thought about how you might handle that? Like, would you try to do maybe global, medium resolution ensembles, since there's some difficulty to just drop in a new domain if there's a new area of interest all of a sudden?
Yeah, that's a really good point. And I think a lot of the value that we provide is at those higher resolutions, because you're able to just capture some more of those tails of the distributions and extreme phenomena. I think Sam Baker has been thinking about this some, but my idea of it would be perhaps we'd have more refined meshes with a global down to refined, and then take advantage of being able to rotate things where we need them to. But yeah, Sam is the MPAS expert. I haven't quite gotten into it yet. So how naive that answer is, I'm not totally sure.
So I just want to comment on that. I mean, if you want two-way interactive nesting, yeah, I think it's a problem, but there's probably some the tools already exist, I think, to actually, if you're running, particularly if you're running a fixed sort of constant resolution grid over the globe, to drop in a one-way nested rather quickly and cut out your pieces. So I think the capability is not everything we want, but there's more there. But I admit that when we talk about it, it's kind of hard to see like how this is all going to go swimmingly, particularly me.
Well, and that's why I'm also very excited that within our squadron, we have, our flight, which is primarily meteorologists, but then we also have our WXS flight, who are our software engineers and software experts, because combining, those two, I feel like we really have the resources to be able to tackle the problem when it comes.
Thank you. Moving along, next presentation will be the Weather on Demand Weather Forecast Framework, Recent Developments and Outlook.
Oh, well, I'll not waste your time trying to learn on the. So yeah, my name is Ólafur Ragnarsson from Iceland, Belgingur, and just want to give you a quick overview of the forecasting framework that we have been developing over the past 10, 15 years. And of course, touch down on some ongoing research and development. So the WRF is a distributed system for many things, but then most importantly, we use it to gather upstream weather data and observations and use it to trigger either scheduled or on-demand forecasts. And the kind of core of the system is the WRF CAM atmospheric model with the WRF DA data assimilation packets. And it can be used to process data for either medium or long-term forecast and storage. Results are made available through APIs, both observations and model data. And model output can also be made available to kind of customized post-processors. And as I mentioned, it's built around the WRF CAM system. Initial and boundary data can be taken from a plethora of global and regional models. The system installation is pretty fast and highly automated, typically assuming that all hardware is in place and configured correctly. Total installation time is of the order of maybe half a day, so 3 to 4 hours. And we can use it to create kind of conventional weather forecast or ensemble forecast. And we have also used it to scale down the CFS forecast. So in operation, we now have a 45-day forecast covering South America, for instance. There is a potential to create very simple text forecasts along a route. And typically output is used as input, for instance, hydrological models or various power production models. I'm not going to go over this. I know the slides will be made available, so this kind of all-encompassing figure can be enjoyed at leisure. The steps to make an on-demand forecast is that we start with the landing page for the Swagger UI. So if nothing particular here, but we go into this meta, we click on the create a job option, and this is where we go into a bit of a detail. We choose the center of the mother of all domains. We choose a predefined model configuration that we have done, and forecast duration and title that can help us locate this again. And this creates a forecast that will have a unique identification number in our database. And if we are happy with the results of the forecasts, we can transform this on-demand forecast into a scheduled forecast with another click of the button option. And here we also choose the forecast duration and a more sensible reference name. And then we can do some more fine tuning in the database, for instance, to choose if we want to have data assimilation and what type of data assimilation we want to do. What we've done lately or in the past year and a half, we are now introducing the hybrid data assimilation option. And this is, as you all know, the 40WAR is very resource intensive, and the Ensemble 3WAR or 40WAR is much more, it's not a CPU demanding. Recently, we have kind of sidestepped or customized the way we initialize dispersion forecasts. So it's more flexible now and opens up the potential of having kind of multiple eruptions ongoing within the same domain. And we can also have a more highly or fine-tuned sources which then feed up into the outer domains. Output from the system can be used as input into the verification packets to compare forecasts. So both from these kind of what we call upstream forecasts and forecasts created within the framework itself. And we're also starting to test using kind of different sources of initial data and the boundary forcing data. And this gives a kind of more potential of blending or making ensemble forecasts. Here's just an example of having two hypothetical eruptions going on. One is inside, or both of them are inside the larger domain, but just one is inside the high resolution domain. Another kind of more real-time or operational case from a recent forecast in the southwest, recent eruption in the southwest of Iceland. We have a 3-domain configuration starting at 400 meters resolution, which is nested within a 2-kilometer domain, which again is nested within a 10-kilometer domain. Just a quick slides of outputs from the WRF solution. Here comparing 2 different models to observations. We also have assembled these kind of XY plots, both for a multiple stations or a single location. Example of the hybrid solution. To the left, we have 24-hour precipitation for South America, fully based on the GFS. And to the right, we have the exact same model configuration with the only exceptions that the initial data comes from the high resolution ECMWF global model. We are now working with a UK-based drone company, testing the use of in situ profiles from unmanned aerial systems for data netting. And we will be following up with testing the kind of surface observations. And then we need to add the option of ingesting Doppler radar data. And we also are working with collaborators in Iceland to have kind of more sophisticated methods to plotting the weather charts. So the drone is called MPAS-JEDI. You can think of it as a flying Roomba. So it has basically this example of a test case we did last year in the UK. This is model resolution in the high resolution domain. Final resolution domain is, I think, 600 meters for this case. And the plot on the right shows the difference in precipitation. So over one day. So there was nothing particular going on in this case, like a non-weather event, but still the effects of the single profiles that were updated every 1 hour or 2 hours has some impact on the precipitation there. The Menapia, the UK-based company, is now operating a UAS on the south coast of this peninsula in Iceland. Here you see the docker or the dock for the drone, and on top of it, I think you see the drone placed on top of it. And this basically goes up to 2 kilometers every hour. And the duration of the flights, ascending and descending, is around 15 to 20 minutes. And they have actually acquired permission to go up to 6 kilometer altitude, as long as they kind of phone in to the aviation authorities with a few hours before flights. Yeah, and this is just a quick map showing the surface observation for Iceland. As we can notice, it's more kind of coastal coverage and very few stations in the interior, which is an ongoing problem. Showing the raters, we have 3 Doppler raters or 4 now, which don't have a full cover of the country, but at least for the most densely populated areas in the southwest. And examples of the plots in collaboration with a small startup company called Ecosophy. So we are trying to mimic the windy look and feel. And there's a good reason for that. They are doing an excellent job in presenting weather data on charts. So to summarize, we can use the system or the framework to create conventional short to medium range weather forecasts, as well as long-term or long-range forecasts or ensemble forecasts. There's an option of using variational data simulation. Text forecast generator is available option. We have the option of using the chemical dispersion option for volcanic gas and gases. The verification packets can be hooked onto the system, and the option of using different data sources or blending different input data sources is possible. And we are of course working on R&D to improve the system even further. So if you have any questions, I'm more than willing to answer. Thank you.
Thank you so much. We do have time for a few questions, if anybody has some.
Hi, I'm Eric James from NOAA. I was curious about the volcanic ash. Do you wait for eruptions before you forecast a plume, or do you have potential plumes that are constantly being simulated in your system?
At least for the current situation in southwest of Iceland, we've been observing quite frequent small-ish eruptions for the past couple of years. So initiating a forecast, we usually just wait for the eruption to start. There is maybe few hours, or scientists are kind of interpreting the seismological data, etc., to kind of give a decent estimate of, say, within the next few days, we might see something happening, and then you kind of pick your ears a little bit and then keep an eye out. These forecasts, they have been starting with kind of the first 12, 24, 36 hours have a kind of high potential, so plume going up to a few kilometers, then they die down. So what I've been doing is just keeping an eye out and listening to my colleagues at the MetOffice and kind of just tune down the amount of both plume height and gases. And we're doing a very short range, so we're doing like 9 to 12 hour forecasts, and we update them every hour using input from the RAP system. So it's coming, more dynamical how we play with the system.
Thank you so much. Leads us to our last presentation before the break. That will be destroying a hurricane and simulating downslope flow with WRF. Lessons from the 2023 Maui wildfire event.
Well, thank you very much. I'm going to talk about probably one of the greatest weather disasters of the last year, and also talk about destroying hurricanes. My co-author is right there, Dave Ovens, and this was recently accepted for publication. So what I'm going to be talking about is the Lahaina fire, the great Maui disaster. And I'll talk to you about the WRF simulation, and I'll also talk to you about how to destroy hurricanes, which is a valuable technology, okay? How do I advance this thing? Just that? Okay. Okay, let me remind you about this. On August 8th of last year, there were a series of large wildfires on Maui central Maui, then on coastal Maui. It killed at least 100 people and resulted in around $5 billion worth of damage. And the historic town of Lahaina was destroyed. And you can see on the pictures there, you can see the West Maui Mountains, you can see some of the grass, and you can see Lahaina, where one house survived, which is an interesting story. Okay, just so to make sure we're all on the same page, and some people have been to Maui here, maybe, but just keep in mind, we have the huge volcano Haleakala, which is around 10,000 feet. There's the highlands around Kula, and then there's the West Maui Mountains, about 5,000-6,000 feet. And then on the west side, there's Lahaina, okay, which was essentially destroyed. Okay, this shows you where the fire areas were. You can see the Lahaina area to the left. You can see the Kula area, the upland areas. There weren't many deaths for the middle area, but all the deaths were associated with the Lahaina fire. And just I want this in your mind. There's the mountains, there's grass, and then there's the town. And basically, this fire was like many of the fires, like the Marshall Fire. It was a downslope windstorm. And strong winds, a grass fire brought the fire into town, and then the homes provided the fuel. Okay, this event was associated with very strong winds. Unfortunately, Hawaii has one of the worst observing systems in the world. It's terrible. The observational assets are terrible. And then what they did have, when the power failed, and the power failed very quickly, they lost observations. It is clear that the winds gusted to 60 to 80 knots in and eastern Lahaina. So keep that in mind. I think that's pretty solid. The damage was consistent with that, including power poles that were snapped off, roofs were taken down, etc. Okay, to give you an idea of the synoptics, and I don't want to spend a lot of time on that today, the synoptics associated with this is associated with an extremely strong high to the north of Hawaii. And I don't know if you can see this little white dot there, where Hawaii. And you can see the isobars. You can see the standardized anomalies with extremely high pressure to the north of Hawaii. So that's really crucial, and that created a large pressure gradient. There also was a hurricane. It's got a lot of publicity. One we're going to kill here in a few minutes, okay? And that's Hurricane Dora. And if you can see the blue there, a very low pressure, okay? That went to the south. Okay, so this is a WRF meeting, and we got to talk about WRF. Basically, Dave did a series of nested runs, going down to 444 meters over Maui, and then it's a 4/3 kilometer domain and a 4 kilometer domain, et cetera. Okay, so this is the resolution that we were throwing at it. Okay, well, one thing I want to tell you is that the forecasts were stunning. The ability to duplicate the winds were stunning. This is a 24-hour forecast and showing you the maximum gusts. And this is near the time of a lot of the action. And the red is the strong stuff. That's like 70 knots. Okay, the 24-hour forecast was perfect. It was near perfect. But the interesting thing is the 90-hour or the 138-hour forecast was also nearly perfect. So this was unbelievably well forecast, very well forecast. Okay, now let's look at some cross sections. Joe Clemson. Oh my God, I needed him. Okay, anyway, I want to show you some WRF vertical cross sections, showing you the winds and also the temperatures. And basically, what we had was a high amplitude mountain wave situation with a substantial hydraulic jump. At least this is what was in the simulations. And I show you this is a series of panels showing you as we move into the period. The winds are indicated by the shading, and the red is the strong stuff. And we're looking at a cross section across the West Maui Mountains. And on the bottom part of the slope there, that's where Lahaina is. I don't know if you can see this very thin gray line that Dave put. That's where Lahaina is. Okay, so we basically had a high amplitude mountain wave and the strong winds descended down. And the model simulation was creating this hydraulic jump. What I'm not going to go to the secret source of this event, but there was extremely strong winds, unusually strong winds, stable air at a perfect level above the mountain. So everything was perfect to give a high amplitude response. Well, Maui doesn't have good observations, but I think the reasons to believe that there was such a high amplitude response. This is from the south. Somebody was taking a picture from Kihei looking towards the region. And I don't know if you can see the hydraulic response. I don't know if you can see there's the West Maui Mountains. The air was going up one side, and you actually had clouds descended down, and you could see the hydraulic jump feature. Okay, and there's other pictures that are like this. Okay, well, stunningly good forecast. But let's talk about some of the new technology that we're going to talk about here. There were many claims in the media that Hurricane Dora was essential for producing this event. Okay, you remember that? Here, just so you believe me, here's a few newspaper, shots. That Hurricane Dora approaching produced strong winds, and that produced this event. Just to give you a little context, here's a satellite picture. You can see Hawaiian Islands, and you can see Dora to the south. There's Dora, and you can see the subsidence associated with the high pressure. You can see that to the north as well. Okay, this is a nice satellite picture. You can see the situation. But you didn't get the impression that the winds associated with Dora was really affecting Maui, right? You didn't get that impression. And the thing is, Dora passed very far south of Hawaii. It was a Category 4 storm when it did so, and it passed 800 miles to the south of Maui. So so the direct effects was that was a stretch, you would think, maybe indirect effects. Okay, so here we go. My mother always wanted me to be a doctor. And so the question is, how can we be a surgeon? So how can we eliminate that hurricane in the WRF simulations without messing everything else out? Okay. As you know, there are many ways of getting rid of hurricanes. There's all kinds of vortex removal approaches. There's potential vorticity approaches, inversion approaches. There's a variety of ways to do it. But we wanted to come up with something really surgical and really subtle to get rid of the storm. Okay, so here it is. As many of you know, tropical cyclones have a vulnerability. They want warm water, and they want water at least 26 degrees centigrade. Okay, so the idea was, well, let's not give it to it. Let's cool the water. So what we did, there's an X across the hurricane, okay? So what we did was 2 parallel 138-hour forecasts, okay? The nominal 138-hour forecast was nearly perfect. So we did one 138-hour forecast where we used the observed SSTs, and we did it. It was a forecast. In every way, it was a forecast, and we used the GFS forecast, on the boundaries. Okay, but we also did another simulation. Dave had a 2-degree box over the storm, and he cooled the water temperature down to 24 degrees centigrade. Okay, just below that, what it wants. And so the storm was followed by this cold water was staying with the storm. Well, and the goal was to weaken and destroy the hurricane. Could we do it? Okay. The answer is yes. Now, what I'm showing you here, the 850 hectopascal winds and heights, that morning where a lot of action was happening. On the top was the control. Now, I know, so I don't know if you can see it, but can you see the hurricane there in the top panel? Right there, you can see, look at the bottom panel. It's gone. We did it, okay? We destroyed the hurricane, and not only destroyed the hurricane itself, but we also destroyed its indirect effects as well, okay? Well, here's the interesting thing. The strong winds remained over Lahaina when we destroyed the storm, okay? So the top one here shows you the control forecast, again, 138-hour forecast at various times that day. And I don't know if you can see the boundaries of Maui. And if you look on the left side, you can see those reds. That's the strong winds going to Lahaina, okay? So the control was really good. The kill hurricane was pretty much the same thing. And so basically killing the hurricane didn't stop the Lahaina fire, the Lahaina winds, and therefore the fire. Now, I'd like to end with something. The downslope winds that hit Lahaina, that was sensitive to grid spacing and, interestingly, to the planetary boundary layer parameterization. This shows you the result what grid spacing does. And again, this is a cross section across the West Maui Mountains, and you see it 12 kilometers, 4 kilometers, 1.3, and 444 meters. Well, it's 12 kilometers. Well, you weren't playing the game. 4 kilometers, we had this kind of shooting flow, but it took 1.3 to get the hydraulic jump, which got better as we got to 444 meters. So I want you to be sensitive to these sensitivity to resolution. But here's one that was kind of interesting. The PBL scheme had an effect too. We tried a number of PBL schemes. We got the downslope. We got downslope winds Lahaina, all of them. But whether you got a hydraulic jump varied. The YSU and the Shinhong are on the top, and they both had the hydraulic jump. But the MYJ and the MYNN just had shooting flow down. It didn't have the hydraulic jump. Okay, so it was an interesting sensitivity to the PPL parameterizations, and maybe some of you have some insights into this. Okay, so this coffee break time. So let me end. The high resolution forecasts were excellent. Okay, at all time scales, stunningly well forecast. And by the way, we've come a long way, folks. Almost every downslope windstorm event, except the Marshall Fire, has been really well forecast, days in advance. I mean, we've come a huge distance. And anyway, if I got controversial, we could have warned these people. And I should say the HER had this, had the solution, and people weren't properly warned. We can surgically remove hurricanes by cooling the waters just around the storm. Dave pulled this off, and it worked extremely well. Hurricane Dora had very little impacts, forget the newspapers, and there was substantial sensitivity to the grid spacing and to the PBL scheme. And with that, I'll end and open up to any comments.
We can start with the online question, if you'd like. Yeah.
Thank you. Someone wants to know the chart where you show where you're comparing the PBL schemes. Which nest was that?
Well, that was Dave. That was the 1.3. Yep, the 1.3 kilometer nest. Yeah.
I spent a lot of time in the Southwest and just taking stuff in from like the T-Rex experiment. It's actually really hard to get like a decently high resolution WRF with decently steep terrain with YSU to not downslope, actually.
Really?
Yeah. So, I mean, it's YSU and high res WRF tend to, it's pretty trivial to get them to downslope. And a lot of times it's overshadowing, over rain shadowing, over downsloping. And so a lot of that's kind of needs to be tempered. But yeah, it's newish versions of WRF can really simulate those pretty well.
Yeah, well, I mean, I've done with Dave, we've done the major wildfires in the last several years on the West Coast, which are almost all of them associated with downslope windstorms. And, we basically get it, So, I mean, I didn't see if we overwarned in other cases. That's an interesting idea. But certainly, folks, we have a lot of skill now in these events.
Thank you very much for the presentation. So it's very interesting that you're able to surgically remove the hurricane and obviously still have the strong winds. I wonder how that affects precipitation and more specifically rainfall.
Yeah.
Looking on to study in the future.
Yeah, I don't know. I don't think we looked at the precipitation effect, but I assume, that all the effects going to be small, obviously. Yeah.
Leave it with one last online question.
Oh, Joe is ready. What does Joe have to say? Z speaking online?
Joe, can you unmute?
I'm trying to. Okay, can you hear me?
Okay, we got.
Yeah, that's very impressive simulations of that hydraulic jump. And I was interested in your simulations at various resolutions where you basically lost the entire downslope event at 12 kilometers. And presumably that's because with the smoothing at 12 kilometers, the mountain height dropped so dramatically.
That's
And
right. You can see the mountain height was much
I
less.
guess you could test that by leaving the resolution at 12 kilometers and artificially maintaining the maximum height of the mountains. But
Yeah.
my guess is you'd probably recover most of the event.
Yeah, I think you're probably right, especially since 4 looked really quite good. So yes, I think that's probably the case, Joe.
But very impressive.
Thank you.
Okay, thank you so much. Yeah, we'll leave it there. It brings us to the end of model applications part 1. So coffee break will go till 10:30, and then we can pick up model applications part 2, the sequel then.
Yeah, I have a quick announcement. About 20 minutes past 10, we'll try to get a group photo in the lobby. So just gather there. We're going to take a photo from upstairs. So just 20 past 10.
Okay, where's our speaker? Is the first one virtual? Oh, here we go. Okay, why don't we get started? Session 6, model applications. The first talk will be by Djougou Xu. Will be the responses of pseudo-global warming simulations to different experimental designs. Okay, go ahead, and I'll stand up when you're 3 minutes out.
Good morning, everyone. This is Djougou Xu from Pacific Northwest National Lab. Today, I would like to introduce our previous work, which provides a guideline for.
Could you move a little closer to the
warming
mic,
method.
please?
The pseudo-global warming method has been widely used in recent decades to examine the impacts of climate change on a historical extreme weather events. Namely, it drives regional climate simulations using reanalysis data, plus climate perturbations projected by an ensemble of global climate models. In this case, it can capture both the historical large-scale circulation and future climate change signals. It can ensure that the simulated future weather event can follow the historical one, thus examining the impacts of a returned extreme event and guide hazard management.
Get closer to the mic.
Oh, sorry. It has several advantages, such as sampling the internal variability and improving simulation accuracy. Although this method is becoming more and more popular, it does not have a precise definition, thus limiting its applications. Several questions remain unanswered. At what spatial scale should climate perturbations be applied? Among different meteorological variables available, which ones should be perturbed? Will PGW projections vary significantly when different perturbations are applied? As a pioneering work, we aim to provide a guideline for the climate community and enlighten the following studies and collaborate peers to improve and standardize this method. This study focuses on the Northeast US, which has been experienced and is projected to experience the most significant extreme precipitation intensification. On the right-hand side, it covers most commonly used PW method. For example, the first one is applying a regional average temperature perturbation, which is used in the original PW paper and following studies, there are other methods such as adding the perturbation of temperature and sea level pressure at the grid point scale. Here is the average regional mean precipitation simulated. Overall, most of methods agree with each other and project that the future precipitation will increase. However, we noticed that if we apply a regional average temperature perturbation, then the precipitation will be overestimated because of ignored land ocean warming contrast. But more interestingly, we find out that if we added sea level pressure perturbation, then the precipitation will be underestimated. However, this method is widely used in many studies, and we will explore why that. Here we can see if we alter the dynamic fields, then the precipitation will be displaced. For example, if we added the wind perturbations, the storm center will move inland. But here, if we look at the temperature field, we can find there is obviously cooling biases in the simulation with sea level pressure perturbation. This is quite interesting because this underestimation will directly makes this simulation deviate from the original warming signals. Here we plot the zonal average warming signals. And we can see that if we add the sea level pressure perturbation, then its warming signal will deviate from the signal projected by large ensemble CSM1. And the biases will can be larger than 1 degree Celsius. We concluded it as a biases because it significantly deviates from what it should be. This can be explained by the hypsometric equation. Namely, for the lowest levels, if the surface pressure, which is P1 here, increase, the average virtual temperature of that layer should decrease correspondingly. And these cooling biases will directly cause less moisture and precipitable water near coastal area, which further cause less precipitation simulated. And here we can see from the vertical profile of warming signals, the biases, the cooling biases, only exist at the lowest levels. This further confirm our previous conclusion that the cooling effect is a biases resulting from adding sea level pressure perturbations. Thus, we would not recommend this method. Then I will briefly discuss the Raspberry wave noises, which has been widely discussed in previous PGW method. However, we found something new. As we said, the original Pseudo-global paper and many following studies apply a regional average temperature perturbation with the assumption that it will not change the original temperature gradient, thus avoiding the unrealistic geostrophic adjustments. However, if we from this animation, we can see that in the historical simulation, the sea level pressure is very smooth. However, in PGW simulations, for example, if we add the regional average temperature perturbation, then there will be obvious wave-like noises along the development of extratropical cyclone. And this can confirm that even if we add a regional average temperature perturbation, geostrophic adjustment are necessary and will introduce wave-like noises. Then we, to better quantify the Raspberry wave noises, we use the Fourier transform. Namely, we by using 2D Fourier transform, we can convert the 2D spatial domain into the frequency domain, and then we can easily quantify its magnitude. For example, on the left-hand side, we can see in the historical simulation, the SLP is quite smooth. However, after we add the regional average temperature perturbation, there are some like wave-like noises, and in its magnitude spectrum, we can observe this high frequency noises, which indicates sharp transition in sea level pressure. And this can also suggest that potentially in the future, we can use Fourier transform to better quantify or evaluate models. For example, we can use it to examine if the model is well initialized, or if the nudging or data assimilation will induce some noises. So overall, we conclude that the PW method is generally robust, although we can observe some stored displacement, especially when we alter the dynamic field. The simulation with regional average temperature perturbation cannot preserve wave-like noises and will overestimate precipitation. We find that modifying geopotential height is unnecessary. And more importantly, adding a sea level pressure perturbation will cause an inconsistent cooler temperature and reduced precipitation. Thus, is not recommended. Finally, we would recommend the simulation with temperature perturbation at the grid point scale, or the combination of temperature and wind perturbation at the grid point scale. The first one can isolate the spatial dependent thermodynamic effect, and the latter one can cover both the dynamic and thermodynamic effects. That's it. Thank you.
Thank you very much. Any questions or comments? Yes, there's an online. Go ahead.
How did you manage the boundary conditions for Fourier transform for the regional domain, which is not periodic?
Sorry, what?
How did you manage the boundary conditions for Fourier transform for the regional domain, which is not periodic?
We can simply use a rectangular box.
The recommendations you have, I think, apply obviously in mid latitudes. What do you think about tropics? Are there other issues that arise in using the PGW method?
Yeah, there are other issues. For example, most previous PW simulations assume that the relative humidity is fixed, and people can only and in this case, people just need to alter the temperature field, then the moisture field will adjust it correspondingly. However, over some areas such as Amazon, the surface drying is obvious. Namely, the relative humidity is projected to decrease. Thus, this method will not hold, and we are currently still working on it.
Any others? Yeah, well, thanks again.
Thank you.
Okay, let's get ready for the next one. Everybody likes a good blizzard. And next talk is simulating blowing snow events in the Northern Great Plains with Polar Wharf. Dave Bromwich will be giving the talk.
Okay. Good morning, everybody. Thank you for the opportunity to talk to you about simulating blowing snow events in the Northern Great Plains with Polar Wharf. This is a collaboration funded by the National Science Foundation between my research group in Columbus, who do the modeling, and Aaron Kennedy's group at the University of North Dakota that primarily do the observations. In the background here is a blowing snow event at Grand Forks, where Aaron is located, to give you a feel for what we're looking at here. Okay, outline, I'm going to talk a little bit about the physics options, simulation results, do some validation, and then a summary and future plans. That's interesting. I had a nice animation and show up.
Try to talk in the mic.
Yeah. Okay. All right. You'll have to imagine my animation. So we're using Polar Wharf, which is a version of Wharf that's been developed and maintained by my research group for a lot of years. And it's been adapted to run interactively with the Bulk 2 moment Pick-Took-D blowing snow model of Derry and Yao. This is a widely used blowing snow model. And basically what happens is the Wharf drives the blowing snow model, and then the interaction comes from the sublimation of the blowing snow, which modifies the temperature, the moisture, and the wind fields in Wharf. During the winter, blowing snow events in the Northern Great Plains can be extreme and life-threatening. To evaluate the coupled model, we focus on this event from 12 February 2020. Aaron has written a lot of papers on this, particularly at Grand Forks, where he is situated. The passage of a very marked cold front on 12th February, the temperature dropped by about 30 degrees C fairly rapidly. The winds jumped up, as you'll see momentarily, to about 18 meters per second, gusting to something like 30, and ground blizzards, so no falling snow onset. We have a variety of observations to check what's going on. Okay, so here's the domain we're using. The area of interest is this Red River Valley, which is on the boundary between North Dakota and Minnesota. Minnesota is the land of 10,000 lakes, which will become important in a moment. South Dakota in the south and Canada to the north. We're using the MYJ PBL scheme, the NOAA land surface model. This, for historical reasons, this is an older version of Polar Wharf. The blowing snow model has 100 vertical levels. You need this to capture the details, particularly the siltation layer down near the bottom. It's got a top of 1 kilometer. We use a threshold of 10 meters per second for blowing snow. We're using the GFS analysis for initial and lateral boundary conditions. Our model resolution is at 2 kilometers. That's important. We have 71 vertical levels with a model top at 10 HPA, and the lowest model level is at about 4 meters above the surface. Okay, we started the simulations at various advanced times in relation to the cold front passage at Grand Forks, which was around 10Z on February 12. Okay, so I work in the polar regions. This is a remarkable amount of observations. I'm not used to this. We have GOES satellite imagery about every few minutes. On the top here, this is visible imagery, so the sun needs to come up. And so starting at about 14:30 UTC on 12th of February is when you see this signature of the blowing snow. And here we go. It's feature here. And the yellow dot is Grand Forks, and you can see the signature is well developed, parallel to the Red River Valley, which is here. The signature shifts east with time, and the clouds at the bottom are associated with the frontal passage. Okay, this is what our simulation looks like with the number concentration that comes out. There's Grand Forks. There's an artifact here for Fargo, which is a big population center there. And here's another artifact of lakes from the NOAA, from the land surface model description. It comes in from WPS. And so what I particularly want to show you is it shifts eastward, associated with this, what happens with the satellite image. The north-south extent is about correct. And we're starting to pick up these things called horizontal convective rolls. And if we went to much higher resolution of the order of a few hundred meters, we would explicitly resolve the detailed structure of these things. Okay, this is the blowing snow mixing ratio. I primarily show this to illustrate these simulations starting to capture these horizontal convective rolls. The accumulated blowing snow transport as time goes on, so it starts from 0 and then adds up the blowing snow as time goes on. The values get bigger, and they're along particularly the valley itself as towards the end of the simulation. The blowing snow goes away according to the satellite imagery at about 18 UTC. This is the 10-meter wind speed. The scale starts to show the colors at around 15 meters per second. And primarily, we've used this gray shade to show features. Pretty good with this. But for example, here you can just see, and particularly here, some of these signatures of these horizontal convective rolls, and they play a big role in wind speed variations, blowing snow variations, precipitation variations within the blowing snow itself. I think I'll skip over the PBL height. Basically, it goes down as the simulation proceeds. Okay, this is, I don't know very much about this, but this is choosable output in WRF, which I believe is radar reflectivity. And this was a reflectivity from a radar. This is Grand Forks, so this was very close. And Grand Forks in this depiction is in the yellow, and this is DBZ. And we're getting about the same thing from the radar at that time. This is a little bit later as the front has moved south. The reflectivity has dropped. Grand Forks is in the sort of light bluish tone, so between 0 and 10, and the radar is showing numbers which are similar. Okay. Because we're in a place with logistics is much easier than in the high latitudes, Aaron's group had a lot of radius zones that they released during this event. So 2 hours, every 2 hours, and these are the ascents. The red is the temperature, the blue is the dew point temperature, and the green is the wind speed. The simulation results are the dashed, okay? And you can see generally the fit is very close, okay? Once the front goes through at around 10Z, there's some differences in the dew point temperature. The wind direction, wind speed fit is overall very close. There's some slight differences down near the bottom. Okay. Here we add the wind direction, and there are some significant differences early before the front goes through, which we're looking into. So these are about 40 degrees discrepancy. But overall, the fit is very close between the simulations and the observations. Okay, here's the 10-meter wind speed. You can see that the wind jumped up very, very abruptly. And the stars, black stars are the observations. Comes out of MYJ is a pretty good match, actually, to the timing and magnitude, a little bit slower than the observations, but the overall trend is very close. This is a gust measured at Grand Forks. We have an algorithm based on U star to estimate the gust from MYJ output. And once again, it's quite similar, but a little bit slower. The pressure field, a very close fit between the observations and the model forecasts. The temperature. The one issue, you can see it at night, is this cold bias that shows up. This is definitely a common feature of the NOAA land surface model at higher latitudes and should be greatly diminished in more recent versions of the model. So that's something we're working on. But, you know, the trend apart from this cold bias at night is quite very close between the observations and model output. This is the PBL height that comes out of MYJ. That's in the colors from the various simulations. And the blues are estimates from the radiosondes based on the vertical gradient of potential temperature. Able to rectify or eliminate most of these when we upgrade to the latest version of WRF with the NOAA MP land surface model. Okay, so summary. So we've done this preliminary work with this case in February 12, 2020. And overall, the bulk observed features of the blowing snow event are well simulated. It's a somewhat qualitative study in the sense of the blowing snow. We want to add wind gusts to the blowing snow module because we think that could have an important impact on how the blowing snow is represented. There is a more advanced version of this PIC-TOOC blowing snow model that has some extra value for visibility calculations. And so we tend to implement that. Perhaps most important, we want to look at additional blowing snow cases that have detailed observations of the blowing snow layer. So as the mixing ratio and particle size distribution as a function of height. A lot of the observations up till now has been at very, very low levels. So that's something that's very new here. And we will be releasing this coupled model to roughly mid-2025, if anybody's interested. And we eventually hope to couple the blowing snow model with MPAS. Hopefully it would be appropriate for use at high latitudes, maybe with a polar suite. I don't know very much about this right now. And so this is a future desire. Thank you.
Okay, thank you very much. Any questions in the crowd? Go ahead.
I was curious about the computational cost for the blowing snow model compared with like just the regular WRF simulation.
It's not very much, you know.
Whole fraction. Okay.
Yeah, I mean, it's of the order of 10, 15%, something like that. It's not, you know, like running 40 bar or something like that, you know, multiplying by 10. No.
Yeah. Okay, thank you.
Any online questions? Okay. Go ahead.
I'm curious, how does the wind gust be calculated, estimated?
Well, yes, obviously it's not an output. So there is various algorithms that you can choose from, you know, that relate the mean wind speed to the gust speed based on empirical observations. So the algorithm we use is based on U star, which comes out of MYJ, but it's fitted to observations. So it's a published algorithm. If you're interested, I can supply the reference to you.
Thank you.
One more, yeah. One small question. We only
Might
have
be.
small amount of time.
There might be something online, I don't know.
Right.
Oh,
You may have said this, but if so, my excuses. But since a lot of these kind of things are really interesting to put into general models, what is the cost of running the drifting snow model compared to the atmospheric model?
it's modest. It's 10-15%, something of that order.
Okay, we got one online. Go ahead.
Wait, go. Been removed.
Been removed. Okay, well, thank you very much.
Okay, thank you.
Okay, Ms. Lloyd, go ahead. Okay, moving on. The next talk will be modeling the extreme July 2023 Hudson Valley precipitation event using WRF and Lloyd Trent of IBM will be giving this talk.
Thank you, everyone. Good morning. First, let me start by acknowledging my co-authors, Tony Prano, who's online, and Mukul Davari, who's here in the room. And let's see if I can figure out how to make this work. Okay, so I'm going to talk about an extreme summertime event. We have Tony and I both live and work in the Hudson Valley area. This event occurred about an hour and a half drive from New York City, for those that aren't familiar with the region. So I'll give some background about the nature of the event, and then discuss our numerical experiments with WRF. This is a work in progress, so we'll discuss where we are and some of the ongoing issues. I'll start with a video with some flooding. This was by some considered a 1 in 1,000 year event. We will, not discuss how statistically accurate that is, but over 8 inches of rain in the region. I'll just stop the video. Important note is where the heaviest rainfall occurred was in and around the U.S. Military Academy at West Point. If you've never been there, it's a spectacular location. They have great summer concerts, which were all canceled last year. This is on an amphitheater over the Hudson River. About $100 million worth of damage. And on the image on the left, you can see some of the flooding on the roads that go through the academy. Lots of damage to local infrastructure and in surface transportation. You can see an example where the Metro North commuter railway was shut down for quite a long period of time, and airport operations were also affected. So here's some estimates of the QPEs. These are gridded QPEs. I just have 3 different ones just to illustrate at this scale. There is some uncertainty, the actual estimates. So the upper left is MRMS at 1 kilometer resolution. The other 2 are at 4 kilometer resolution. So there's the NOAA AHPS, the upper right, and PRISM at the bottom. Just as a side comment, I have a small weather station at home. I observed 4.5 inches of rain, which doesn't correspond all that well to what's in the QPEs. So just as a side comment. So as some background, at this particular time, it was very moist conditions, mostly from tropical air that had moved into the region, that then was blocked by a relative high. You can see in pointer to work. Oh yeah, so you can see the omega blocking here in the analysis that blocked the tropical moisture. And then in addition, the shortwave trough to the north and west, this led to training convection, during the day on the 9th of July. I should also mention another factor related that led more to the flooding. If you're not familiar with the region, the topsoil is relatively thin. This is mostly because of the glacial retreat, and because of typical, but a little on the high side of a rainfall over the previous few weeks, the soil was quite saturated. So a thin layer soil saturated, when the heavy precipitation occurred, flooding ensued quite rapidly. And just as an example, some of the data that I'll show. So West Point is here. And then a couple of the New York State mesonet sites are marked in yellow, just for context. Down in over here is the location of the Upton WFO. So the radiosonde launch there is about 108 kilometers from West Point. Again, for those not familiar with the area. So here's an example of observed rainfall. This is just for the 9th of July, not going into some of the rain that continued earlier overnight. This is from the site in Beacon, which is the closest on the New York State mesonet. This is 15.6 kilometers from West Point. So total precipitation observed there was 4.83 inches. But as you can see, some rather high rain rates that evening. And actually for this particular site, that's the most that's been observed. And this site's been in operation since 2017, 2018, something like that. So again, anecdotally, a very high rainfall rate. So there's one of the profiler sites is at Suffern, about 30 kilometers from West Point. And this is SKU-T animation, coming from that site. We're actually already going into the next day. Let me just back that up. So, and notice the cooling in the upper air as we move into the 9th of July and where when the heavy rainfall started to occur. And we're going to get back to this point a little bit later. So now let's talk a little bit about the predictability. So here we see information from the NOAA Weather Prediction Center. So this is about 12 hours before the event, showing moderate risk for the region. And again, talking about this area here. The image on the right is showing the output from the operational HER. This is for the HER run at 12 UTC on the 9th of July. So this is about a 12-hour lead time. And you can see, some predictability for the event. But let's put this into some context. So, so what we're starting up here is, and I have a little annotation down here, but here's again the MRMS QPEs. And so moving backward in time, so this is the 18Z HER on the 9th of July, 12Z, 6Z, 0Z, and then going back, to the full range of what the 48-hour HER operated. So this is 8th of July at 12Z. And then if we want to go back further, we're then going to the high-res NAM, and this is for 8 July 0Z, where we can see the degradation of predictability as we move back in time, as we'd expect. And then essentially no scale from NAM, 8th of July, 0Z. So that's where we're going to start with numerical experiments. So the question is, can we introduce better predictability for this class of event? So I'm going to go a little bit of detail on our WRF configuration. We're running three domains, 9, 3, and 1, and running a set of 72-hour hindcasts in this case. Physics configuration is outlined here. Our experiments are going to be with different microphysics schemes. The way we are configuring this is we're using, since this is operating as a hindcast, we're using RAP for background fields, and then we're using the hourly GFS for lateral boundaries. And then various NASA data sets for surface parameters in the initialization. And so again, we're going to initialize at 0 UTC on the 8th of July. So just to put the configuration in context, so you can see the 3 nests. We are doing data assimilation of conventional observations. So the gray boxes are showing sites available through MADIS, and the dark red boxes are showing those from the mesonet, and then just showing this in a little bit more detail. So the entire New York State region and all of the New York State mesonet sites are within the 1 kilometer nest. So these are the 4 schemes that we worked with: Thomson, WDM6, Morrison, and the predicted particle properties. So just to outline the differences and the similarities, so the parameters that are common to all of them are underlined. Those that are unique to specific schemes like WDM6 Morrison and P3 are highlighted in red. And a few differences that, so Thomson and WDM6, as you know, interacts with RTMG. And then P3 is introducing ice riming and deposition to compute combined particles. So let me show some results. So we're going to focus on precipitation. So again, back to the MRMS. This is the output with Thomson microphysics. We can see we don't really capture the heaviest precipitation. We're also getting significant displacement as well. We can look at this in a little bit more detail to see how well this works or doesn't work at specific locations. So in this case, looking at two sites, the two nearest New York State mesonet sites at Beacon and Somers. And Somers is, the Beacon's the one I showed before. Somers is 18.6 kilometers from West Point. So here we just have some simple plots. It's a function of the model time in UTC. Blue line is observed from the mesonet site. Red line is showing the model. You can see that timing for start and stop is not too bad, but obviously the precipitation amounts are significantly low, compared to observations. The next experiment is with WDM6, and you can see the skill is hardly any skill. So we'll skip that. So with Morrison, we have a bit better than WDM6, but still significant displacement, and the highest areas of precipitation are also missed compared to MRMS. And then the final simulation is with the P3 microphysics. And here we're starting to see a region, captured with the amount of precipitation in comparison. There is a sort of a false positive to the southeast, but there's still significant displacement compared to where the heaviest rainfall occurred. So we can look at this with some of the specific sites with the mesonet data. So here again, those same two closest sites, Beacon and Somers. Certainly with Beacon, it's pretty good in comparison. Timing corresponds fairly well, and the totals are only off by an inch. Of course, compared to any of the others, that's significantly closer. But now, if we look at Somers, we can see how significantly, how much we missed in that location. And this, of course, is related to that displacement I mentioned earlier. And if we look at two other sites to the northwest, we can see that, as well, pretty good on timing, low bias in the precipitation. We can put all of this in context for all the experiments, showing the QPs, Thomson, Morrison, WDM6, and P3. And one of the things that we're interested in understanding, is the role of ice riming with P3 and then warming leading to more rapid melting. Is that leading to better precipitation estimates? So this is some of what we still need to study. So we're encouraged by some results that show some level of predictability with a model that's initialized 48 hours before the actual event. And the most realistic results we're seeing with P3. Despite these limitations, we do see better skill compared to the operational models covering the region. And want to acknowledge University at Albany and New York State Mesonet, whose data were critical to run these experiments and to evaluate them. As I mentioned, this is work ongoing. So we will be doing additional simulations to look at the predictability, especially with the lead times, and also doing further analysis as well. We need to examine the hydrometeor profiles to understand more about the microphysics contributions to the precipitation. And we'll apply the same methodology to other major events in our home state of New York. With that, I want to thank you for your attention. I guess we have time for a question or two.
Yeah, we'll put a question. Thank you very much. Questions? Anything online or? Yes, there is.
So first they wanted to tell you nice QT animation.
Okay, well, I want to thank Nathan Bain from the University at Albany for providing that.
Do you attribute this issue more to the model parameterization or to the quality of the ICs provided to the model?
Well, we have not done sensitivity on the initial conditions for this particular study. So right now our emphasis is or assumption is focusing on the microphysics. It's certainly a very reasonable thing to do for further experiments. We've used that combination for a number of years in both operational modeling and in INCUS with good results. So that's why we started that way.
One more.
Wanted to ask, what was, or did you examine any of the differences in the runtime between the 3 microphysics schemes?
It's a good question. The differences were relatively small. Granted, the computation was dominated because of the large 1 kilometer nest configuration. So within 10% of each other. If we had run simpler microphysics schemes, WSM6 or simpler ones, yeah, then there'd probably be a much larger difference in runtime.
Great. Well, thank you very much.
Thank you.
Okay. Finally, the machine learning talk. So the next talk will be an experiment in hybrid weather prediction for downslope windstorms, and Rob Fauvel will be giving the talk.
All right, thank you very much. So as I'm sure you know, frequent wildfires have motivated to the establishment of large public utility mesonettes. The figure here at left shows about 3,000 surface stations that have been deployed in California alone since 2008. These point observations and forecasts are used for public safety power shutoff decisions, that's PSPS. PSPS forecasting is very important. It's not something I want to do because I like to sleep at night. The consequences attached to wrong decisions are potentially enormous. But PSPS forecasting and decision making will benefit from long lead times because of for situational awareness, for staging of resources and warning the public, high resolution modeling because of the complex terrain in the Western United States, and ensemble forecasting for uncertainty. So because many of these things cannot be satisfied with our current operational models, many utilities now perform or support their own NWP efforts, and including WRF and increasingly MPAS, but these needs conflict because it requires a lot of resources, and oftentimes resources are limited. So I've been trying to think about ways of increasing efficiency in utility forecasting, and I'm thinking I'm going to propose something like a last mile modeling approach. Instead of running 1 kilometer, say, WRF simulations out to the medium range, like 4, 6, 8 days, use tools to identify future threat windows and initialize WRF simulations from forecasts instead of analyses. These tools could be like self-organizing maps, AI machine learning type things trained against past threatening events. This leaves more resources available for ensemble forecasting, and it may be able to better utilize ensemble spread from operational products, and I'd like to talk to people here about. But what I really want to do is I want to utilize AI machine learning weather prediction models that have been emerging recently. These are capable of global 10-day forecasts in about a minute or so, which is very efficient. But these are still pretty coarse resolution and not directly useful for PSPS forecasting. And of course, they're not useful at all unless they have some skill. And the scary thing is actually they're pretty good. So what I'm going to do is I'm going to demonstrate downscaling a machine learning weather prediction model, specifically Google's GraphCast, using WRF and a last mile approach. So last winter, it was a cold and icy day, and I'm sitting in my chair and I'm thinking, why can't we do this? And so I decided to try. So let me illustrate the last mile approach. The horizontal axis is time. picturing an operational model like GFS, one of the ECMWF models. It's running out into the medium range. Our typical practice is to take the analysis and initialize WRF and then run that out. We may be running the model for days and days of boring weather, and boring weather at high resolution is still pretty boring. But let's say that near the end of this window, we know that there is a threat emerging from our for forecast tools that are based on the synoptics. So thinking about maybe just initializing WRF at the beginning of that window, okay, if we can identify it properly, and initialize off maybe GFS forecasts at that time instead of the analysis. But the real reason I want to do this is I want to take a similar analysis and initialize GraphCast with that. The great thing about GraphCast is it's going to run very, very fast, and it's going to get to the threat window very quickly, and then I'm going to initialize WRF from that. Okay, so that's basically what I'm going to try to do. So GraphCast is one of several machine learning weather models that have appeared recently. It was trained on ERA5 reanalysis. It shares its quarter-degree lat-long grid, which is too coarse for wind forecasting in the Western US. It provides most, but not all of the fields necessary to initialize WRF, and some software modifications were necessary. The experiments shown here, and we have a paper in review on this. The GraphCast was initialized with the ECMWF high-res products, which I needed permission to get some of the stuff used for this from ECMWF, using their AI models Python package with missing fields provided by GFS. Okay, so my use case is going to be the Marshall Fire windstorm, which occurred near here a couple of years ago. I'm going to use WRF simulations at 3-kilometer grid spacing, largely mimicking the current version of the HRRR. WRF will be initialized with GFS, ECMWF's high-res, ERA5 reanalysis for a retrospective look, and also GraphCast. So here is a picture of 400 millibar geopotential height, winds, and wind speed at the time near the event maximum. During this case, you can see a narrow trough extending from southwest to northeast across the domain. If you look at the inset at the lower right, that's showing you the area of Colorado. The star is where the Marshall Fire started, and you can see there is large horizontal wind shear in the domain, stronger winds in southern Colorado, weaker winds at this level in northern Colorado that turned out to be very important in this particular case. So I'm going to show you longer range forecasts of those same fields from two different models. I'll reveal the models in a moment, but this is the 30-hour forecast valid at the same time as the previous slide. And the main thing is they look very similar, and it looks similar to the last figure. You have a narrow trough going from southwest to northeast, and it's bisecting the state of Colorado with stronger winds equatorward and weaker winds poleward. Let's go forward. 78 hours prior to the event maximum, still looks pretty good. The two models are starting to lose the picture a little bit. You kind of expect that, right? And going out 102 hours, now you're seeing more loss of skill, but one of these is actually subjectively and objectively better than the other. It's the one on the left. That's GraphCast, okay? And the one on the right is GFS, okay? This is, I have mixed feelings about this actually, but I'll just keep going, okay? So the details, subtle details are important in this case. This is zooming in on the area of Colorado. Again, the star is where the Marshall Fire started. This is the field analysis at the time or around the time that the event reached a maximum. You can see strong winds in the southern part of the state, but just at the location where the fire started and to the north, those winds are significantly weaker. It was very important here because that allowed an environment that was conducive to developing the downslope windstorm. A longer period simulation valid at the same time had a subtle error in the positioning of where the strongest horizontal shear was. That ended up with a windstorm that was weak, delayed, or even non-existent. So this is pretty important. I'm going to focus on an area here that includes where the Marshall Fire started. I'm going to call that the target area or area of interest. We can divide our territory. If you're a public utility, you're going to divide your territory into a whole bunch of areas of interest. They could represent individual circuits or groups of circuits or places where wildfires have been a problem in the past. This is just one of them, okay? And I'm going to show you now, these are a depiction of the fastest wind speeds during the event seen by the models that are going to be used to initialize WRF. Clockwise from the upper left, that's ECMWF, GFS, ERA5 reanalysis in the lower right, and GraphCast at the lower left. Warm colors mean fast wind speeds. You're not seeing very much in the way of warm colors because these models are not capturing the strong winds. That's why we downscale. These are the WRF versions of downscaling that. They're much better. Actually, they're all pretty good, but some are a little better than others. But you know, this is why we use that, okay? So I'm going to focus on GraphCast here. This is the GraphCast forecast that was used to initialize WRF. And I'm going to pose a question. Can GraphCast simulate a downslope windstorm? There are no dynamics in this model. It's analog forecasting on steroids. I stole that line from Cliff Mess, okay? So what do you think? Well, here is a vertical cross section from GraphCast, not downscaled. Those black contours are isotropes. If you see those plunging down on the east side of Boulder, you've got a downslope windstorm, and that's as close as it gets, okay? So I think the jury's still out, but I'm going to vote no. I don't think this model can actually do that, which means there's still jobs for the rest of us in the future, okay? I'm going to downscale that starting at the 84-hour forecast with WRF. WRF is going to produce a really good downslope windstorm that is very realistic with respect to timing and spatial extent. So that's a pretty good result, okay? So I'm going to evaluate, I've got lots and lots of forecasts, and I'm going to try to evaluate them using a scorecard approach. Okay, so this is complicated, so let me walk you through it. The horizontal axis is initialization time, the shortest lead time at the top, lead time increasing towards the bottom. Horizontal axis is time period during the threat window. Each individual box is going to be color coded with the maximum wind speed in my area of interest during the simulation. Warmer colors are going to be faster winds. I hope to see lots of warm colors in the boxes with the X's because that's the time period during which observed sustained winds exceeded 50 miles per hour. And at the right, I will have a summary of the judgment of what is coming from the forecast. Okay, so either alarm level, which is the highest level of threat, alert, caution, or no perceived threat. So this is last mile WRF forecast initialized with ECMWF operational products. And what we can see here is the shortest lead times, no threat is detected, okay? However, at medium lead time, several days out, there was actually a pretty good forecast. So the forecast degraded as the event got closer. Boy, that's a problem, isn't it? And if we go even farther out, the event started too early and it was not really very well developed. But basically, this is what we got here. On the next slide, I'm going to show you the GraphCast forecast. Oh, I've converted this into a score in the lower right, and this is a score of 6.25. What does that mean? It's less than this one, okay? Oops, sorry, what am I doing? Okay, so this is last mile WRF initialized with GraphCast, okay? So what we're seeing here is a whole lot more warm colors in the boxes where the X's are. Those are forecasts that are very good with respect to wind speed and timing. And most of those initialization times are actually warning me that something is coming, and it isn't losing the picture as the event got closer like the other one did, but that's why you want to do ensemble forecasting, right? To try to get a measure of what the uncertainty is going on, okay? So this has a total score of 8.5. So let me summarize this. This again is just for one location. We know where the fire started, so that's why I'm focusing on that. But if you're your utility operator, you're looking at your entire service territory. And again, the horizontal axis is initialization time, and the forecast column at the left is color-coded. What is the assessment from GraphCast initialized WRF? Okay, and this is the most skillful amongst the examples that I'm showing here. And again, I want to say I have mixed feelings about that. Okay, yeah, I think it just kind of shows how much farther we need to go with respect to numerical weather prediction. But the numbers don't really matter. It's gauged by how good the forecasts are with respect to timing and location. Okay, so you want to see red boxes because those are essentially good warnings. And that is the most skillful. The second most skillful combination here was WRF initialized with GFS forecasts. Okay, the third most skillful was WRF initialized with GFS analyses at the initialization times listed at the left. Okay, the best one overall, perfect in every respect, is WRF initialized with the RA5. Okay, now of course you don't have the reanalysis and too far after the fact, but what this is showing you is the benefit of a good initial condition of nothing else. Okay, so it's the initial conditions made the difference here in high quality forecasts. GraphCast seem to give you a little better synoptics than some of the other alternatives here. Okay, so let me summarize. This is a hybrid weather prediction approach. I wanted to use the word hybrid because everybody uses it and it's kind of cool. Okay, but what I'm trying to do is I'm trying to combine a AI machine learning weather prediction model with basically with WRF. GraphCast to WRF or MPAS. I haven't tried MPAS yet, but I think I can figure out how to initialize MPAS with this. Requires some extra fields and software modifications. GraphCast-driven WRF simulations appear to be competitive and can add value to a forecast ensemble. From one example use case, I'm not going to conclude that it's always better. I don't want it always to be better, but I do want it to be skillful. I will post details to my nearly blank GitHub page after my paper is accepted. So if you're reviewing it, please be nice to us, okay? Thank you.
Thank you. Maybe time for one question. Okay.
So now that you've played with GraphCast a bit and now WRF, so the question would be, why don't we train AI on higher resolution data sets then, since we can do that once and use it many times instead of having to continuously run expensive NWP?
Okay, so you're trying to put the rest of us out of a job. I suppose that can happen. My gut feeling, so I come from an NWP background. I don't really know how these models, these AI models are done. I actually don't want to know, okay? I want that to be someone else's job. But my feeling is I'm not sure it's ever going to get the right answer for the right reason. I have feelings for why it's actually better on the synoptic scale. It is really constrained by what has happened in the past. WRF, you're integrating every few seconds, you're computing more tendencies, you're projecting those out. It can go off into places that it's never been explored before and never should be explored, right? But GraphCast takes two 6-hour fields, two fields 6 hours apart, and kind of says what happened the last time we had something like this. So it's not clear to me it's really going to produce anything new. And it's not clear to me that if it got a downslope windstorm, it got it for the right reason. It'll be just because there was some kind of picture in the past that kind of looked like that. So I don't think it's going to replace mesoscale and smaller scale, convective scale anytime soon, not in my lifetime. Not in your lifetime. I don't think that's going to happen. If I'm wrong, by that time I will be dead and I won't care.
I suggest to the people who run this meeting that we should have a session on just this issue next year. There's a lot to explore here, and another issue that having training data sets at high resolution. So there's a lot of very interesting things. Next year we need a session on this topic. Anyway, I think we better move on.
Okay. Thank you.
Okay, let's move on. The next talk will be modeling superstorm Ida's precipitation over the New York metropolitan area using WRF. And Jorge Bravo will be giving this talk, and I guess this will be done remotely. So go ahead.
Yeah, thank you. Can you hear me?
Yes, we can.
Okay, thank you. Hello, everyone. My name is Jorge Bravo. I'm PhD student at the Stevens Institute of Technology. It's located in Hoboken, New Jersey. Well, today I'm going to talk about my work. Is what I'm developing is modeling superstorm Ida precipitation over New York metropolitan area using WRF. Well, before starting, I want to thank for the opportunity to be part of this WRF MPAS workshop. I'm user of both models, and I really like to update. And space like these are the best, of course. Well, this talk will be described following these points: introduction, the study case, objectives, the study area and data, methodology, describe one of the metrics used, show another couple of metrics, show a comparison of rainfall accumulated and grid-based evaluation, the results, and the next steps. Well, as introduction, New York Metropolitan Area is one of the most important American metropolis in the country for its population and diversity. And due to its geographical location, this city can be affected by high latitude and tropical system, or in some cases, a combination of both. Global scale models such as GFS or mesoscale models like NAM generally provide a good overview of the area. However, for a local point of view is not enough. A city needs to have a forecast with a high resolution, high spatial resolution. Also, this data can be used for another purposes, like input for hydrological models, for instance. Yeah, well, here in this image, I try to show the surface analysis when Ida was, well, the post-tropical cyclone Ida was over the New York metropolitan area. Well, the study case, tropical cyclones are one of the main causes of extreme flood events in the U.S. Northeast region. Well, Ida enters the United States and impact in Louisiana as Hurricane Category 4 on August 29. However, the system was weak after entered to land. It combined with an surface front and upper air throw, and it causes it continue with this high convective. The primary factor favoring the intense precipitation was the transition from the tropical to extratropical system, and it happened between September 1st and September 2 on 2021. Here in the image, I try to show the track of the Ida impact here in the United States, and when it moved from here to the Northeast region, it combines with this front, and that was the reason because it continued with a convective activity. Well, what are the objectives of my work? Develop a regional tailored weather forecast system, improve the local scale weather forecast for New York metropolitan area, get a high resolution of meteorological variables, focuses with a precipitation estimation, and automated weather forecast system that can be used for informed decision making. What is the study area? This is the perspective of our study area. Of course, it's the New York Metropolitan Area. We have 3 different domains to run the work model. As you can see in the figure, we have the outer domain is in blue box, is the regional coverage, and it has a 9 kilometers of resolution. The middle domain in green is for the state level overview, and it has 3 kilometers. And the inner domain in the red box is the most significant of this work and has a local scale resolution of 1 kilometer. For this work, we use ERA5 analysis to generate different simulation scenarios and perform the sensitivity analysis. After we identify the best scenario, we use GFS forecast data to reproduce again the forecast for IDA. Also, we use a weather station from NOAA, from Mesonet New York, and Mesonet New Jersey for a point-based evaluation, and also MMS data for the same period for a grid-based comparison of accumulated precipitation. Here in the image, I am showing the 3 domains, also the land cover in the New York Metropolitan Area, and the most of the stations used was differentiated in non-urban and urban kind of stations. The methodology is with this ERA5 analysis data, we ran the work model version 4.4.2. In the period August 31 to September 2 was the period of IDA in this region. Also, we use the default configuration of work, and then also we run 9 times. The results from these 10 scenarios were evaluated with weather stations and MMS observations. Urban and natural environment sites were considered to evaluate the performance of the HS scenarios as function of the landscape, and the accumulated rainfall were calculated from work simulations and MMS data in the period of between September 1st and September 2 for the spatial assessment. Here in this table, I will show you all the combinations used for run WRF in these 10 different scenarios, and in the lower table, basically what is the name of each option in the schemes. For the evaluation, we consider use until 10 different metrics. Here are the names: time peaks difference, the Kingley-Gupta efficiency for KGE, KGE skill score, percent bias, root square, root mean square error, normalized root mean square error, mean absolute error, and max error. Based on the latitude and longitude of each meteorological station, we select the most closest mesh grid cell to extract the time series and compare with the series of the observation in each station. And here we can see in the X axis each station, and in the Y is a scenario. So we can identify here what are the best metric. In this case, for KGE, we considering a good agreement between 0.5 and 0.7, a better agreement between 0.7 and 0.9, and the disagreement between 0.9 and 1. So in here we are identifying the simulation as 0.4 as the best, with most of the good agreement values, and for the non-urban areas also we are considering the best the simulation 05. Then we have for all metrics similar heat maps. This is for time peaks difference. We try to identify what is overestimated, when is underestimated. For the peaks difference values, the magnitude of the precipitation, also we have some similar heat maps, and all 10 different metrics we have this kind of heat maps. Related with the accumulated rainfall, we compare it with MRMS and H of1 of the simulation for scenarios. Here we have the MRMS as base or benchmark. Then we have the default work combination of current work, and then H1 of the scenarios to display to show the difference between the accumulated in the same period. The period is between September 1st at 00 UTC and September 2, 23 UTC. So based on this grid-based evaluation, we extracted each grid cell between each scenario and the MRMS to extract time series. And also we create this kind of maps, but for metrics, and extract. Then we count how many pixels or grid bases are urban, what are water, what are cropland, what are forest, and others. And we identified again here in this grid bases that for us the S4 is the best for the urban area.
2 minutes.
Okay.
2 minutes.
Yeah, it's fine. The results are world rainfall simulation show a better agreement with urban site observation when urban physics scheme was activated. The correlation results show a good agreement with urban station from Masonet, New York, compared with Masonet, New Jersey, and say NOAA. Similarity for the non-urban areas, a better agreement was obtained with the Masonet, New York station. The accumulated precipitation results show a general tendency overestimate MRMS observations. And according to the different metrics evaluated in all the scenarios, in general, all metrics show that the scenario number 4 was better performance. Next steps, automated system for forecast using GFS as input, run model twice a day, get forecast 103 hours forecast, and same 3 domains. And thank you so much. If you have some question, please.
Thank you. Thank you. And any questions from the crowd here? No. How about online? No questions. Oh, one question. Here we go.
I'll just quickly comment that for people who are looking to run the urban, the multi-layer urban canopy model, that we have that hooked up to MYNN PBL now. So you have an option of a probably better working PBL scheme with the full urban model. That's still in development. We have a student working on it, but it's working. So.
Great. Well, thank you very much. Any other?
Thank you very much for the comment.
Okay. Well, thanks a lot. Okay. The next talk will be a WRF-based system for forecasting high impact weather for our Northern California power utility. And Richard Carpenter will give this talk, and it's going to be virtual. So go ahead.
All right. Thank you very much. Pardon me, I've got a cough. I do my best. I appreciate the opportunity to speak to you this morning. I want to acknowledge my colleagues at DTN, at Pacific Gas and Electric Company, and at TechnoSilva. We are interested in high impact weather. in Northern California. And chief among that, of course, is wildfires. California is obviously prone to the wildfire threat as much of the Western United States. PG&E has developed a fire potential index model that is driven by the WRF model. It's also driven by dead and live fuel moisture data analyses provided by TechnoSilva, which is also driven by the same WRF model. We've heard about public safety power shutoff. It's been implemented following the devastating 2018 Camp Fire. Since then, in one incident, nearly 1 million customers were de-energized. Obviously, a tremendous inconvenience, and you have to consider that the lines have to be inspected before they can be re-energized, and so just a tremendous inconvenience. And so they fine-tuned that, developing an enhanced power line safety settings wherein a circuit is de-energized when a fault is detected, such as a tree falling on a line. And that provides a much finer tuned setting. So the goal of what we're doing here is to make the best possible WRF model that can feed into these downstream models that can enhance PG&E's decision making. So when they can address these various threats. So we call this POMS, the PG&E Operational Mesoscale Modeling System. We've been at it for 10 years. We started with WRF version 3.5 and a 3-kilometer grid. We're down to a 2-kilometer grid using WRF version 4.1, and we're currently testing a version based on WRF version 4.5, and that's what I'll spend most of the time talking about. Our current version has a 2-kilometer nest. We go out to 5 days, 4 times daily for the deterministic and twice a day for a stochastically driven, stochastically perturbed set of ensembles. We started off with a 30-year reanalysis for training the downstream models. And every year we accumulate another year. We initialize that reanalysis in August 1st of every year. As I mentioned, these are input into TechnoSilva's fuel moisture and also their ignition models. One interesting feature, we've got a web launched or a GUI that you can launch your own on-demand 0.67 kilometer nest. So as an example of that, on the left, you have a 2-kilometer grid over much of Northern and Central California. On the right, you have that 0.67 kilometer nest. This is not used operationally. It's just used occasionally by the forecasters to get a better handle of what's going on. And this was an extreme downslope event in October of 2019. Well, what our motivation, as I mentioned, we want to test the latest version of WRF. It's been over 3 years since, well, close to 4 years since we've done this. We know that models generally get better over time, right? There's been new capabilities that have been introduced or refined, such as irrigation. And we also want to get away from our stochastically perturbed ensembles and instead use a GEFS as our basis for initializing our ensemble. So those members are going to be selected using cluster analysis, and we're going to try and capture the full diversity of the ensembles using fewer members. So our ensemble set may be as few as 9 members, for instance. And then we'll rank the results of that by mean and percentile. Just irrigation was something that we worked on. I thought it might be interesting to those here. In NOAA MP, it's driven by the GeoGrid data, by the MP table. The nameless settings, had to get those from a Git commit. So, but we're triggering irrigation based on the crop growing season. Obviously, we don't have any fine-grained control over that. In our 5-day tests, we typically saw irrigation depths of up to 30 centimeters. And it did improve the dry bias on those dry summer days. We're still on the fence about whether we want to turn this on. We're not sure how it's going to behave over a long term or over the course of a reanalysis year. But it did provide good results in this case that I'm showing in the Central Valley and the adjacent Sierra foothills. Our process for going through this validation, we have 6 high impact cases that we've selected. And for each one of those, we're going to do a 5-day WRF simulation. And then we're going to pick the 48 or 72-hour validation period around the time of the maximum impact of the event. We have a number of experiments where we varied the model version, the various settings, the model initialization. And we're initializing with the GEFS or GFS runs that would have been available 2 or 3 days prior to the event. That gives us some realism as far as realistic errors that we might see. As noted earlier, there's an extensive mesonet set of mesonet observations upon which we can draw. PG&E's meteorologists have flagged a set of trusted stations that we're going to use. The variables that we're looking at, 10-meter wind speed, we're not doing any anemometer height correction just to keep things simple. And we're looking in 3 categories, all wind speeds and any speeds over 5 or 10 meters per second, because in a lot of what we're looking at, it's the high wind speed events that are critical. We're looking at temperature. We're also looking at vapor pressure deficit, which unlike dew point, it's a conserved quantity. It's also used in a newer fire weather index called hot, dry, windy. Here's the cases that we've selected over about a 4-year period. Some of these are, well, most of them are some combination of hot, dry, and windy. There is a late winter storm that we've also selected as a high impact event that involved heavy precipitation. Just to give you an example, this is it's a classic downslope event. It's the one where PG&E de-energized almost 1 million customers, classic event where you have northeast downslope winds traverse to the Sierra Nevada and coast ranges. I'll step you through this complicated slide. First of all, we're ranking our runs as we change our version from 4.1.2 to 4.5.2. This is not apples to apples. There are some configuration differences, but it's what we use operationally versus what we're proposing to use operationally. And then going on to finer resolution. So looking at the bottom 3 here, all speeds. So WRF has a slight high bias, speeds greater than 5 meters per second, pretty slim bias. And then you look at speeds greater than 10 meters per second, WRF has a low bias. And we consistently see that these things improve as we go to the newer version of WRF. And again, the configurations are not identical. And then as we downscale from 2 to 1.5 to 1 kilometers, for the wind speeds, for temperature in the upper middle, the bias actually gets worse as we go to 4.5. We're not exactly sure why that is. It's a little bit concerning, but on the other hand, it's something that with machine learning biases can be addressed. Now we're looking at the GFS deterministic, which is on the left of each one of these panels, and then various GEFS driven ensemble aggregations, whether that's the mean of the GEFS initialized runs or the 25th or 75th percentile. And so what we find is that for wind speed, the 75th percentile or the mean is going to be the best. And for temperature and vapor pressure deficit, the 25th is going to be the best. So again, this is a slide looking at the different cases, and they're labeled by month and year, and then there's a little key here, you know, hot, dry, windy, or just windy. So WRF has a fast bias at low wind speeds, a slow bias at higher wind speeds, and then it also has a warm and dry bias in the summer and fall cases. That tends to be negated somewhat for the here's a January, a February, and a March case.
2 minutes.
The as we here's a summary of the changes that we've made. Notably, we've changed our version of MYNN. We've added gravity wave drag. I think we probably just overlooked that on the previous configuration. We're on the fence about irrigation, and we've introduced a new ensembling technique. And then finally, here is just a summary slide describing our results. Please contact me if you have anything that you might be interested in finding out, or if you have any comments. So thank you.
Thank you very much. Thank you. Any questions in the crowd? I got one right here.
Thanks. Jared Lee from NSF NCAR. I'm wondering if you could comment more on the initializing from the GEFs from the 25th percentile, 75th percentile. How are you defining those percentiles? Like what variables, what scores, et cetera?
Well, in these cases that we've done, and we can slice and dice the verification results as we want. It's really just let's say for wind speed, we're going to take the highest 75th percentile. So of the 9 cases that were or the 9 GEFS members, we're going to take the 75th percentile. That's not saying it's how we're going to do it in operations, but for these results, that made the best. And so the ranking is just in terms of RMSE. So in other words, we're correcting for a low bias at the high wind speeds.
Okay, well, thank you very much. I think we have to move into the final talk of the session. Okay, the last talk will be comparison of simulated and observed radar reflectivities at, I can't even say it, Djougou, on September 22nd, 2006 during the AMMA campaign. And Justin Kuamel will be giving the presentation. So this is online. So go ahead with that.
It looks like our next speaker is not online.
Thank you.
Okay.
Thank you.
Is our speaker online?
He showed.
Well, thank you.
Oh, thank you.
Okay, We can hear you, but we can't see any presentation.
Oh, sorry. Can you hear me now?
We can hear you fine.
Okay.
You can't see the screen at this point.
Okay. Thank you very much. And good afternoon, everyone. My name is Kofi Justin Kwame, and today I will present to you our work on the comparison of simulated and observed radial activity at Djougou in September 22, 2006 during the AMMA campaign. This work is done in collaboration with François-Xavier Bobela from University of Nangui Abrebois in Abidjan, Côte d'Ivoire. Next. Here are the outline of our study. First, we'll present you the introduction. Next, I will present data and methods used for the study. And following, I will present the main results and discuss them. Finally, we will conclude with our funding and future perspective. Precipitation variability has significant impact on the economy, health, and quality of life of a population. So understanding, monitoring, and qualifying precipitation is crucial for weather forecasting, risk management, and decision making. Rather, reflectivity is an important tool for improving quantitative precipitation estimate and monitoring convective system and precipitation patterns. Unfortunately, there is very little meteorological data available in this region for precipitation estimation. Therefore, numerical.
We're advancing your slides. If you can let us know when to advance them.
What?
We are advancing your slides. If you can just let us know when to advance them.
Okay. Okay. So I was saying that the precipitation have impact on variability. The precipitation variability has an important impact on the health, the quality of life and population. So it is necessary to understand, monitor, and qualify precipitation water forecasting, risk management, and decision. And the use of radar reflectivity is important for improving quantitative precipitation estimate, monitoring of convecting system and precipitation patterns. Go on. Unfortunately, there is very little meteorological data available in our region. Therefore, numerical simulation is a necessary alternative for improving the accuracy of weather forecasts, integrating radar real time, and validating model performance, or studying the meteorological process that influence precipitation. In the other hand, in our region, more than 80% of precipitation is provided by Squall. So it is necessary to test numerical model as WRF by studying with rather complex convective systems. The purpose of this work is to test the ability of WRF model to simulate radar reflectivity fields associated with precipitation produced by the Squadron in September 22, 2006 during AMMA campaign. So we aim to compare radio reflectivity field simulated by those observed by the X-band radar position in Djougou, Benin, West Africa. Additionally, we seek to determine the model limitation and suggest possible improvement. Let's now see the data and method used in our study. Thank you. So our study covers an area extending from 15 degrees east and 20 degrees west, and from 0 degree north to 25 degrees north. We use the study domain is what you are seeing here. So from 0 degree to 25 degree north, and from 50 degree west to 20 degree north. The data we use is analysis data from the National Center for Environment Prediction, and the radar reflective field were observed by X-band radar in Benin. Let's continue. Okay. Numerical model used is WRF version 341. And this table shows the different options and terms used for the model configuration. It includes numerical integration, turbulence, convection shear, microphysician, planetary boundary lander, radiation, surface layer, land model, and lateral upper layer boundary conditions. The simulated prediction now. The model is initialized on September 22, 206 at 18 UTC and constrained every 6 hours on the lateral boundary of a domain. The duration of the simulation is 2 hours and integration time is 120 seconds. We use 3 grid, 3 Nelson grid, 3 Nelson grid to simulate. Grid 1 that covers the entire domain with a resolution of 27 kilometers. Grid 2 intermediate area with a resolution of 9 kilometers and grid 3 centered in Djougou with a high resolution that provides the description in wind, the description of the process in wind emissions, particularly microphysics. This degree will be used to study radar reactivity. Yes, you can see that. And now, after the presentation of data and thresholds, let us present our results and discussion. This figure shows the radar radioactivity field simulated by WRF and those which are observed from the radar, the X-band radar position in Djougou. On the first line here, we have simulated and
3 minutes left. 3 minutes.
the second line shows the other one. Okay. This result shows that this one. So this result shows that radar reflectivity range from 6 dBz to 48 dBz for simulation and from 10 to 40 dBz for observation. Though there is a standard difference, we can say that the values are on the same magnitude. But the model did not simulate well radial resolution. As regard to the spatial and temporal distribution. We can see that on this figure that the simulated radial resolution is there is a gap between the simulated radial resolution with the observed ones. And this can be attributed to the poor representation of precipitation formation process in the model. The biases in input to data are such as initial condition and meteorological forcing. The result highlights the importance of selecting the right combination of model parameterization scheme. Many other authors have found the similar result. In conclusion, we can say that our study compared radar radioactivity file simulated by WRF model to those observed by X-band radar in Djougou. The result shows that although the reflectivity radar factor is roof in the same order of magnitude, significant discrepancies exist in the spatial and temporal distribution. Further study should focus on improving the representation of precipitation formation process, adapting geographical parameters, and reducing biases in initiation and forcing data. Thank you for your attention.
Thank you very much. Are there any online questions or comments?
I'm ready for.
Okay, well, thank you very much. I think we're going to end the session at this point. Okay, thanks for everybody attending. Okay.
All right, welcome to the final session of the workshop. This is new applications with MPAS. There are 6 15-minute talks. I believe the yellow light goes on at 12 minutes. At that point, I will stand up by the microphone, so that will be your cue. The first talk is virtual. It is being delivered by Colin Grudzian, and he's going to talk about MPAS versus WRF twin experiments. So when you're ready, Colin.
Great. Yeah, thank you so much for the opportunity to give a talk, and thank you very much for the opportunity to present virtually. It's really well appreciated. Today, I'll be discussing efforts at the Center for Western Weather and Water Extremes and with our collaborators to develop an ensemble forecast and verification framework for WRF versus MPAS twin experiments. What I'll start off with is just a discussion about the operational missions at CW3E, where particularly our main programs are the AR Recon program, the FIRO program, delivering situational awareness, and transmitting research to operation. And then we'll discuss how West WRF, the internally developed WRF suite, along with integrated atmospheric river forecast verification metrics, together support all of the above missions. We'll then look at how MPAS is seen at CW3E as an eventual successor to WRF, and how we see specific use cases for MPAS in terms of ensemble forecasts, high resolution atmospheric river simulation, and data assimilation impacts. This will bring us into some specific contexts of where we're developing multi-model forecast skill assessments for key atmospheric river forecast metrics, in particular with WRF versus MPAS ensemble twin experiments, WRF GSI versus MPAS-JEDI data assimilation twin experiments, and specific interest in terms of data impacts in utilizing the MPAS-JEDI system for atmospheric reconnaissance, as well as airborne radio occultation data impact studies. Finally, we'll just give a quick statement about code development and availability. So the Atmospheric River Reconnaissance Program, or AR Recon, is led by CW3E and NCEP, and is a research and operations partnership designed to improve AR predictability at lead times of 1 to 5 days. CW3E and collaborators plan reconnaissance sampling in areas of data gaps, where you can see, for instance, in the figure below, an actual reconnaissance flight, two of them, given by a NOAA G4 and an Air Force C-130, where the flight patterns with the dots and squares are where drop zones were released over an atmospheric river, as shown by the IVT plume in the figure. Research at CW3E seeks to maximize the impacts of these AR Recon data sets, where you can see a typical drop zone profile on the right, as in situ measurements are taken by the drop zone as it passes through the IVT plume. CW3E also provides precipitation forecasts for individual watersheds in order to optimize reservoir management with the program that's known as Forecast Informed Reservoir Operations, or FIRO for short. In particular, CW3E currently delivers numerical weather prediction forecasts tailored to different watersheds in order to help reservoir managers actually optimize their releases, their actual water levels with numerical weather prediction, rather than using, let's say, just statistical climatology, as has typically been done historically. CW3E also develops and provides forecasts for situational awareness to address decision-making needs of sponsors in the state, local, federal, private contracts that we run, with a hallmark example being the AR scale developed by CW3E and collaborators, similar to the hurricane scale, but which is a factor of both the AR duration over land and the maximal IVT magnitude of the plume. Through research to operation, we integrate the state of the science, model physics, and uncertainty quantification in our West WRF modeling suite to deliver near real-time forecasts to address sponsors' forecast data requirements. And thus, CW3E's core missions are supported by West WRF and integrated atmospheric river forecast verification metrics. The 200-member West WRF Ensemble and the West WRF deterministic forecasts being run at a 9-kilometer resolution in terms of the ensemble, and the deterministic forecasts with the additional 3-kilometer nested domain in WRF are provided throughout the West Coast wet season to deliver these forecast products with both utilizing 60 vertical levels. And in addition, these products are extended by research that we perform at the Center in AI and machine learning. We provide actually deep learning and AI-driven post-processing, with a key example being the CW3E 200-member ensemble post-processed by deep learning algorithms to deliver enhanced corrected forecasts for precipitation to the California Department of Water Resources. So through our West WRF modeling and AR forecast verification, we deliver uncertainty quantification of extreme events, particularly focused on atmospheric rivers and Santa Ana winds, which are related to heavy precipitation and fire weather, respectively. Integrated model verification of atmospheric river intensity, landfall, and timing and location, and precipitation accumulation, or respectively temperature, humidity, wind speed, and lightning, together provide feedback, which improves our modeling system and improves our basic science, and by which we're able to provide actionable products to our stakeholders. A key aspect of how we actually perform forecast verification at CW3E is that we rely very extensively on the model evaluation tools framework of the DTC, for which you can see the sort of conceptual diagram of which typically MET can be run with the MET plus Python wrappers and drivers to take various valid times, lead times, and different models, run them through the MET engine, and produce plots, diagnostics, and additional post-processing. But in order to meet, let's say, our specific needs in terms of AR forecast skill assessments, as well as the needs of our near real-time forecasts, we also heavily modify these workflows internally in order to run, let's say, a performance system with our specific metrics. A hallmark example of how we've utilized the MET framework, specifically with the MET mode tool, in order to deliver forecast verification products, is with the measure of effectiveness developed by Laurel Dahan and others, which is a measure of the object location, both in space and time, throughout the AR evolution to determine the accurate storm tracking with the IVT. So, as we start considering and evaluating MPAS for our operational needs, there's a variety of ways that this assessment is benefiting from CW3E research projects and projects with our collaborators. Specifically, we're considering how we want to configure sort of an AR MPAS. We're configuring MPAS for enhanced atmospheric river prediction in the Western USA, CONUS, and globally, as well as how to use MPAS for high-resolution atmospheric river simulation, both for basic science needs and for AI model training. Likewise, as we consider a sort of successor to the West WRF Ensemble, we're contemplating how to design effective ensemble forecasts in an AR MPAS suite. And we have specific interest in MPAS-JEDI for data impact studies to enhance AR recon, where in particular, let's say the global configuration of MPAS has a lot of benefits in terms of removing the boundary condition contamination when we want to run data denial or data addition studies for data impact assessment. Likewise, it offers the opportunity to have high-resolution simulation in targeted regions, both for our reconnaissance and for the downstream impacts in the mountainous precipitation regions, and thus facilitates enhanced studies of data reconnaissance and how to maximize the benefits. Likewise, JEDI is the framework that includes the Scripps Institution of Oceanography's modified ROP operator, which allows airborne radar occultation assimilation within JEDI. So, as some examples of how our research is sort of developing this framework for evaluation, we'll look first at how high-resolution AR simulation using MPAS-A can be used as the basis for predictability experiments and AI model training. In the figure below, we see work of Alison McKellis et al. Studying a 30-year nature run and comparing the climatology of MPAS-A versus AR5. This was generating a 30-year continuous MPAS-A dataset from the 1st of October 1989 to the 30th of September 2019, with 15-kilometer global resolution and six hourly outputs. And it's found with this work in preparation that the MPAS-A configuration reproduces accurately the mean climatology compared with ERA 5. Likewise, as we assess WRF versus MPAS in an ensemble context for our sort of West WRF ensemble, we are doing some extensive study of similar configurations between WRF and MPAS, where, let's say, heuristically, we might consider the off-the-shelf 60 to 3 kilometer refinement very similar to the West WRF nested domain 2, and the 60 to 10 refinement very similar to the parent West WRF domain 1, in which we want to look at, say, quantitative and objective skill assessment between similar configurations of WRF and MPAS on our key metrics and compare these to operational global model skill to determine our value added of these systems. In this case, looking at accumulated precipitation for AR events versus PRISM precipitation and stage 4 precipitation. IVT is one of our other key forecast metrics. And so amongst the diagnostics that we're developing ways of comparing WRF versus MPAS versus, for example, ECMWF forecasts in the short range, and for historical studies versus ERA 5 reanalysis to determine discrepancies from reanalysis storm track. Likewise, CW3E's WRF GSI MET workflows have previously facilitated AR recon data simulation studies with the legacy WRF GSI system to compare skill versus global models to ensure that we're achieving an operational skill. And we are planning currently to convert these to Silk for further comparative studies versus MPAS-JEDI, utilizing a unified framework with the M-cubed MPAS-JEDI cycling workflows to compare MPAS-JEDI versus the legacy system and global model skill. As mentioned, airborne radio occultation is a key interest of our center, in part because at very little additional cost to the reconnaissance flight, it adds a lot of high quality data that's of similar quality to the drop zones, but also have qualitatively very different profiles, allowing us to get much greater measurement coverage of atmospheric river development and to hopefully optimize these flights. The verification that you've seen already has already been partially integrated with the M-cubed JEDI MPAS workflows, which has facilitated some analysis of data impacts of ARROW, as you might have seen in Need Do's poster and the work of the Haas Lab currently at the conference. And a full suite of AR forecast skill verification metrics are planned to be integrated within this JEDI framework. So codes are currently available on the CW3 GitHub under the UCSD open source license. Though we'll note that documentation is currently limited due to its early phase of development and these pending Silk rewrites. But collaboration is very welcome, and closer integration with the M-cubed MPAS-JEDI Silk workflows, as well as the DTC Met plus Python wrappers, are both planned so that we can have a full AR case study suite. Questions, inquiries for collaboration or availability can be sent to myself or to our research director, Luca Del Menache. And so thank you very much for the opportunity to talk.
Okay, we have plenty of time for questions. Okay, going once. Anything online? Okay. Can you talk a little bit about what are the challenges in implementing MPAS for your experimentation?
I'd say in part, the early development of physics suites. One of the key aspects of the West WRF Ensemble is that it's actually a full multi-physics suite, and for which there's been extensive work on the modeling team at CW3E to produce a variety of combinations, both in terms of physics and as well as things like stochastic perturbation through SCEBS to really enhance the ensemble variability to get this robust uncertainty quantification that we try to achieve with this 200-member ensemble. Because of, let's say, the comparatively early development of physics suites, as well as things like SCEBS in an MPAS framework, the horizon, let's say, at which we can actually adopt MPAS to achieve that full, let's say, amount of variability we try to achieve is a foreseeable limitation, though part of the work that we're trying to outline here is a framework so that we can objectively assess, how we can develop new physics suites and, let's say, achieve comparable skill with the West WRF Ensemble.
Okay, thank you very much. So our next speaker will be, and I apologize for messing this one up, Djougou, okay, who will talk about hybrid 3D EN bar in MPAS-JEDI.
Thank you. My name is Djougou BJ, and today I will talk about the effect of variable dependent localization and static B in the hybrid 3D EN bar configuration using MPAS-JEDI. Yes, so MPAS-JEDI is data assimilation system for MPAS model, building on a joint effort for data assimilation integration software framework. So in its variational application, it serves the minimize the cost function in an incremental formula shown here. So I want to briefly talk about the analyzed variable of MPAS-JEDI is zonal, meridional wind, temperature, and here specific humidity and surface pressure and hydrometeor content at the cell centers. And in its background covariance, the hybrid B can be defined as a linear combination of multiple covariances. So for example, it's a sum of linear combination of static B and ensemble B. And this does not necessarily be two of them. It can be multiple B, and also the sum of weight can be different from one. So it's quite flexible. Here, I'd like to briefly introduce our static B design component. So maybe I cannot describe this all in detail, but MPAS-JEDI static B uses bump from Saber, one of generic component available from JEDI, and linear variable changes from MPAS-JEDI. So we factorize the static B is a linear multiple submatrices, and here so this K1 is a linear variable change from stream function and velocity potential to zonal and meridional wind, and in this K1 part is specific to MPAS-JEDI repository. So this operator works directly on the native MPAS mesh. The other components are here. K2 is a vertical cross variance variable covariance using linear regression, and the sigma is a diagonal matrix with the error standard deviation, and the center of the C is a black diagonal matrix representing univariate spatial correlation. So at this point, the set of variables becomes a stream function, unbalanced velocity potential, unbalanced temperature, and in this currently the specific humidity and unbalanced surface pressure. And all of these K2 sigma C components are using the bump which is available under Sabre in JEDI framework. Oops, sorry. Yes, so the issue is this is how it operates, and most of these components requires some specific parameters such as regression coefficient and standard deviation or some of length scales. So the training of these, we need to train these static B parameters, and this requires applying inverse operator of K1, K2, or sigma to some training samples. Also, we need to diagnose the spatial correlation lengths. So in this talk, I compared two set of samples. They are all NMC type of samples. So it is forecast differences of difference forecast read time verified at the same time. So here I use the 40-hour forecast minus 24-hour forecast. And one is a GFS-based samples. It directly uses GFS 40-hour, 24-hour forecast files interpolate to the MPAS meshes. And the other one is MPAS-based samples. So for this set of samples, I initialized MPAS model from GFS analysis and integrate 40-hour MPAS forecast, then define the forecast differences. So also we need to Also, we need to tune the diagnosed parameters. So, because there are some inconsistency in our assumptions and characteristics of samples. Here we reduce the horizontal correlation lengths for wind variables by half, and also we rescale the error standard deviation for all variables by 1/3. This is, here I present one of the parameters, which is a regression coefficient at the northern mid-latitude. So x-axis are stream functions and y-axis are temperatures. So for a given stream function forcing, it creates a warm and cold perturbation above and below that level. So this relation explains some of those mass and wind momentum balances in the samples. So when we compare these two, there are some similarities and differences, but overall they match it very well in the mid to lower levels. But we can see there are a lot of large signal near above the tropopause. This slide also compare the other static B parameters. So these are horizontal correlation lengths and vertical correlation lengths and error standard deviation between two set of samples for the stream function, unbalanced velocity potential, unbalanced temperatures, and specific humidity. So overall, I see the correlation lengths agreed well, and the most distinction between two samples are these error standard deviations. From MPAS-based samples, especially near the mid to upper level, the error is larger compared to GFS-based samples. One of the hybrid B components are from Ensemble. So Ensemble B's are some of localized Ensemble perturbations. So here L is a localization matrix. Again, we are using bump Nicas for these localization functions. And in our experiment, the ensemble samples are from pre-generated 80-member MPAS-JEDI EDA ensembles, and they are some of the experiment details here. And in this talk, I compared two sets of localization. So one is applying single localization length for all variables, and the other is applying different localization lengths for different set of variables. So, for example, if we use the same localization function for all variables, so this let that here, that we place the Dirac delta function and multiply that localization function. In that case, the localization function looks like basically the same for both temperature and cloud water field. But if we apply the two different, here the only differing the horizontal lengths, then if we place the same temperature Dirac delta function here, the localization function to the other different lengths looks like this. So the magnitudes are decreased, and also the spatial patterns are also reduced. So we did a 1-month cycling experiment. The nonlinear state is 30-kilometer global MPAS meshes, and the increment, the actual minimizations are done at 60 kilometers. So this also means the meshes for static B and ensemble Bs are at 60-kilometer meshes. We assimilate a bunch of observations, including all sky MCA experiment, MCA observations. So the benchmark experiment, we used GFS-based B and used the single localization functions. And so in the second experiment, we applied variable-dependent localization, and third experiment, we replaced the GFS-based B as a MPAS-based B. And lastly, we applied both things. And the hybrid weights are basically 25 from static B and 75 from ensemble. But because GFS-based B does not have hydrometer content, they are coming from ensemble 100%. So here is some summary of aggregated result. So for the background field, which is a 6-hour forecast, we verified with respect to GFS analysis. So these y-axes are model level and x-axis are latitude. So this is aggregated RMSEs for each variables, and the color shade shows the relative RMSE changes. So red means RMSEs increase and blue means RMSEs are decreased. So, and here the numbers are the maximum values of these color bars. So here overall, we can see the variable dependent localization is beneficial, especially for the south hemisphere regions. And second, if we use the MPAS-based static B parameters, it's remarkable. It improved a lot, except some of tropical region near the model top. And again, if we include both effects, it is quite similar. And here I added relative impact of variable dependent localization when we using MPAS-based B. So still variable dependent localization shows some benefit in the mid to lower levels. And we did a 5-day extended forecast, and again, we see the benefit from variable dependent localizations and using own bees, static bees. Yeah, so for summary, so from 1 month cycling experiment, we have found the importance of good static bee parameters. So yeah, I don't know exactly what could be good, but I can say which reflect the characteristics of a given forecasting system well. So the given forecasting system can be defined differently for each purpose. So yeah, the users can put some effort to get a good estimate. The other thing is we can find the benefit of variable dependent localization, and the cost increased about 50%. So because if we use different, especially shorter localization lengths, that requires more memory and computations. So here I listed ongoing and future effort for improving these in general. So yeah, again, we can do better. We can seek better training of static bee parameters. And also we can try some of vertically varying localization lengths, or we can even diagnose the localization lengths from training samples, or even diagnose the hybrid rate. So these four bullets are all already available from BUMP. So, and there are also other generic capabilities from Sabre, such as spectral B or explicit diffusion B. So this can be also explored further. And more importantly, yeah, for community users, we will provide a script or set of tools, and including document to training static bee parameters for MPAS-JEDI. So maybe in next MPAS-JEDI tutorial. Yeah, thank you.
Okay, we are at time, so we'll move on to the next talk. Chao Sun will tell us about all sky radiance assimilation.
Good afternoon, everyone. My name is Tao Sun, and I will give a talk about the all-sky satellite radiance estimation using MPAS-JEDI's LGDCAF. And here I will thank my colleagues for their help in this work. So in the past several years, many efforts have been dedicated to developing MPAS-JEDI with various assimilation capabilities, including the deterministic assimilating approaches as introduced by BJ and Jake Liu on Tuesday. And also MPAS-JEDI has the ensemble data estimation capability. There are currently two approaches available. One is the ensemble of data estimation, that is the EDA, which update ensemble members by solving the minimization of variational cost functions of all EDA members. So it is quite expensive one. And another one is the INCUS-based method. Two variants. One is the local ensemble transform Kalman filter, the LEDCAF, and its gain form, the LGDCAF. So both methods only compute the common gain once, so it's much cheaper. And in the recent 2 decades, the cloud and the precipitation affect satellite radiance had been successfully assimilated in the global NUDAP centers and shown very promising results. And MPAS-JEDI also has the capability to assimilate all sky side radiances. And the paper Liu already shown a very positive impact on the deterministic forecasts. And in the INCUS-based methods, the side radiance assimilation is a little bit challenging, just because that it is the vertical integrated measurement. So it's very hard to define its vertical coordinate. So make the problem for localization in vertical. And the LGD-CAV experiment, LGD-CAV method can do vertical localization in model space with modulated ensemble members that estimated the vertical localization matrix. So it is very suitable for radiance assimilation. So to enable the all-sky assembling capability in MPAS-JEDI's LGD-CAV, we have used the CRTM as an observing operator and also convention of the variables and hydrometer matching ratios as variables, so that we can simulate the radiances under all situations. And also we made use of the various functions within UFO to do quality control for like the pre-QC, background check, signaling, and others. And also very important is that to do bias correction for radiances. So here I show the correction for the correction rate is the relating to the YBC coefficients, and we got those YBC coefficients from our deterministic DA experiment. So it's an offline bias correction, and also for all-sky assimilation, the situation dependent observing error is introduced to model the observing error of all-sky radiances. And this table shows the assimilated clear sky MSA and the MPAS channels, as well as the all-sky window channels from MSA at different satellites. And we also added the LGD-CAV and ensemble data assimilation capability in our MPAS workflow to conduct an ensemble DA experiment. So the left shows the flowchart of the how we do LGD-CAV analysis. So we can see clearly that the total procedure was split into three key steps. The first one is to compute the ensemble O minus B, and following the second step to do the analysis and updating the ensemble members. And the last step will calculate ensemble O minus A. And so the reason why we split to three steps is that we want to make use of efficient round robin distribution for calculate O minus B and O minus A. It can save a lot of resources. And for calculating ensemble O minus B, we have optimized the procedure that we can see. We first calculated ensemble mean HX and then use its QC flex to reproducing the UDA5 for assimilation. So the size of the observations are quite reduced, and this contribute to much reduced computation cost in the following steps. And and when calculating ensemble HX of all the ensemble members, we improve the job strategy. And we do it with multiple parallel jobs, and each job handling one member or a subset member. So all this treatment has improved the computational proficiency, computational efficiency of the LGD-CAV analysis. And here is the model configuration and the experiment design of this research. So we use an older version MPAS-A model, which has 55 levels with a more top set to sit 30 kilometer, and using a cost unified 60 kilometer global mesh, and using the method scale reference suite for parameterizations. And in LGD-CAV, we have a total of 18 members initialized from the ensemble members of a time lagged GFS, and we have simulated the conventional observations. All right. And we have simulated conventional observations, and also clear sky MSA and MAS radiance, and all sky, and some most experiment we simulate all sky radiance from MSA window channels. And we do 1 month cycling with 6 hourly assembling interval. So for the vertical localization, we do it in model space using the LGD-CAV with a scale of 6 kilometers in height. And for horizontal localization, we do it in observing space. And for vertical localization, we have used 11 engine vectors for each member to account for 95% of the vertical localized matrix. So we have a total of 880 modulated members for vertical localization. And here shows the experiment. The top two experiments are 1 month experiment for final evaluation. And the other 4 experiments that with different inflation parameters and different horizontal localization scales for the all sky window channels. So these 4 experiments are only 10 days cycling, just for sensitivity test for optimization. So first, let's see the sensitivity of the inflation. So currently the MPAS model doesn't well consider the mode uncertainty. So the covariance of inflation is very important. So we have 3 experiments here, either using the RDPP alone or RDPS alone, or using them as a combination. So for the solid line, it is ensemble spread. We can see that either using RDPP or RDPS alone, we do see the trend that the RMSE, the spread gradually reduced with assuming cycles, and a combination of RDPP and RDPS will maintain the ensemble spread, and correspondingly, we can see that the combination could produce much smaller ensemble mean RMSE. And this result is very against the GFS analysis. And we also test the sensitivity of the window channel radiance horizontal localization scale. We see 3 different localization scales. So the left one is for the localization scale with 1,200 kilometer, and the other 2 is its percent of RMSE reduction compared to the first experiment. We can see with a smaller horizontal localization scale, do see the RMSE are reduced, particularly in the south hemisphere. Yeah, this improvement particularly due to a slightly higher spread in these regions. So yeah. And with all those optimization, we do 2 1-month cycling LGDK experiment with and without all sky simulation. So here shows the ensemble mean RMSE reduction of the 6-hour forecast of all sky relative to the clear sky. We do see that for most variables at most regions, we do see that RMSE reduction means an improvement. However, we still see some degradation on temperature, particularly in the southern hemisphere. And after detailed check of the result, we do see that in the southern hemisphere, we do see the larger reduction of ensemble spread in here, so that it partly explains why the RMSE are increased for temperature and also for QV in that region. And this slide shows the 7-day forecast, and we to service the computation cost, we just initialized to the 7-day forecast from the ensemble mean, and still can see that for winds and humidity, we do see RMSE reduction, and the improvement can last for 7 days for U and Q, yeah, particularly in the tropical regions. And the degradations in as shown in period 6-hour forecast, that the degradation temperature lasts only the first 3 days, and in later days, we can even see some improvements in some regions. And we further do verification against the observations. So the left is verify against the radio sound, and the right is verify against the 9 channels of the ATMS radiances under all situations. So the verification against the real sound, the conclusion very close to that in the model space verification. Improvements in wind and Q, degradations of temperature. And while verify against the ATMS radiances, so we do see for not for wind channel, over water, or either temperature or humidity sounding channels. We do see improvements that reduced RMSE, and this improvement can last for 5 or 6 days. And we also use the ensemble forecast in both LGD-CAP experiment to estimate the ensemble BC and provide it to the hybrid reading INWA. So yeah, we can see we have 2 experiments here. One using the ensemble BC from the kilo sky and one from the odd sky. And we can see also verify again the JV analysis for the 6-hour forecasts. So for almost all variables and in almost all regions, we do see the errors are reduced when using the odd sky generated ensemble BEC. And so last, just give a conclusion here that the LGD-CAP in OOPS has been implanted to MPAS-JEDI and is employed to estimate all sky radiances in global MPAS model. And we have improved in computation efficiency of MPAS-JEDI's LGD-CAP, and with improved analysis procedure and job strategy in our MPAS workflow. And we also do sensitivity experiment to improve the performance of MPAS-JEDI by tuning the ensemble covariance and the horizontal localization scale for all sky radiances. And the all sky estimation of MSA wind channel radiances has improved both 6-hour and 7-day forecasts, and also improved the deterministic DA by providing a better ensemble BC. So we are also exploring to do the LGD-CAP at a higher resolution, like 30 and 15 kilometer on global mesh. And in the near future, we are also explore to assimilating high frequency, high resolution infrared radiance and the radar data using MPAS-JEDI's LGD-CAP for regional and convection allowing or MPAS model. So yeah, that's all I have. Oh, thank you.
We might have time for one short question if we have one in the room or online. Okay, if not, thank you.
Thank you.
Our next speaker, Andreas Prine, will tell us about severe extratropical cyclones in the Northeast US under climate change.
Welcome, everybody, and thank you for allowing me to speak today. I want you to take a deep breath and rewind your brain because we are changing topics. This is not forecasting. This is more climate change and downscaling that we're talking about, specifically extratropical cyclones in the Northeast. It's, I think, a very timely topic. If you followed the news this spring, there were 2 really major events hitting the Northeast, specifically Maine. This is one of them, January 13th, extratropical cyclone caused devastating storm surge. This was record-breaking, and you can see, oh, doesn't advance. I have to, but no.
You are using your own laptop.
I'm using my laptop, yes.
Yeah.
And I advance in my laptop.
Huh. Try resharing.
Sorry for that. Oh yeah. So this was the cyclone that I talked about. Devastating storm surge, and extratropical cyclones can have similar wind speeds in this region and also similar storm surge to tropical cyclones, but are way less understood how climate change impacts those cyclones. So the goal of this project is quite ambitious. It's trying to get close to 100-year return value of extreme wind speeds from extratropical cyclones in the Northeast. That's really difficult, especially if you think about local scale wind speeds, so high resolution modeling. The way we approach this is we use the CSM2 large ensemble data set. So many of you might have never heard about this. CSM2 is a CMIP5 style model. It's a climate model, a system model that we develop here at NCAR. This large ensemble is a a combination of 100 simulations. They basically differ only in the initial conditions. And then you have exactly the same forcing and you repeat the same simulation 100 times, you get different weather and you can look at 100 times, for example, the same climate period, the weather. So you have a large amount of data that you can look at and a large amount of weather that you can look at. The ensemble is covering 50 to 2100, very long period, 250 years with the SSP 3.7 emission scenario. This is quite high warming. This is also what I show you down here at the bottom. You see it's going up to 6 degrees global warming until the end of the century, CSM being a hot model. It's 1 degree grid spacing, so you have to run cores to do that amount of simulations, of course. And there are 10 members that have sub-daily output that we can use to downscale. So those are the 10 members that we will focus on. So, but there are three surprises in this project that I wanted to point out. The first one being CSM is producing quite realistic extratropical cyclone tracks in the Northeast. So here what I'm showing you is just one ensemble member. These are hundreds of cyclones. I use a cyclone tracker to follow cyclones, identify and follow cyclones similar to extratropical, to tropical cyclones. The left one plot showing ERA 5 coarsened to 1 degree grid, so it's the same grid spacing as Lens 2. And the right one, just one member ensemble, and you can see many tracks. All of them go through this square here. And what you can also see if you do a little bit more statistics, the track density looks similar, but Lens 2, the CSM is a little bit high, approximately 10 to 20%, too many extratropical cyclones, but overall, it looks quite realistically. What's even more surprising is that the characteristics of these extratropical cyclones in this very coarse model look quite realistic if you compare it to ERA 5, if you coarsen ERA 5. So you can see the cyclone minimum pressure is almost identical between the two models. This is the low pressure in the center when it passes through the box. Also, the movement speed is quite similar. It's maybe a little bit slower in the climate model than in the reanalysis, but quite comparable, and the size is also very similar. You also see the year-to-year variability. Here you can see again the little bit upward shift, so a little bit too many extratropical cyclones, but also the variability from year to year is quite realistically simulated. So quite happy with these results. What we did then, we used the MPAS model to downscale these individual cases, and we use quite common setup, 55 vertical levels, the deep convection suit that was presented before, the only difference being that we used a new Tietke convection scheme. We only do 3-day-long simulations, so we start with initial conditions interpolated from Lens 2, from the climate model, and then let the model freely run. And the extratropical cyclone is hitting the Northeast in the second day. We test 3 meshes to do the downscaling, the first one being the 15 to 3 kilometer mesh, and the 15 to 3 kilometer mesh, the circular mesh and the elliptical mesh, and then the 60 to 3. The biggest difference here is really the number of horizontal grid cells. Here you have 8 million, and here you only have 800,000. So there's a factor of 10 difference. You can also see this in the runtime, whereas you need 21,000 core hours on economy, and the ratio to do this simulation, you only need 1,800. So it's 10 times cheaper or more. Also, the storage volume is much cheaper, and the runtime, of course, as well. So we try to see if we can get away with 60-3, or how different the results are compared to running on different meshes. So let me show you one example just to illustrate how MPAS is doing with downscaling these storms. So what you see on the left-hand side, Lens 2 only had 6 hourly data, so this is quite chunky on the left-hand side. We saved hourly data for MPAS. This is the initial conditions. You basically just see the same field. This is sea level pressure and contours, and the colors are the wind speed at 850 hectopascal. So we just interpolate, and then we start the downscaling. It takes a little bit to spin up this, the simulation, but after a couple of hours, you can see quite nice structures emerging in MPAS, as you would expect. This is the first time we really detect the cyclone. This is basically the initiation of the cyclone that would hit the Northeast. And you can still see, if you look at these two pictures, they're very similar on a large scale. If we move forward in time, when the cyclone is intensifying quite rapidly, no, I just try to, yeah, this is the same time. The colors are not too bad. What you see now is really that MPAS is producing a very nice sharp cold front here, and it also produces a warm front over here, which is completely missing in the lens 2, because it's just too coarse. So MPAS can really create very realistic looking mesoscale structures from very coarse resolution data. And I also want to point out like the orographic effects here. Of course, they're not in the lens 2, but you can see this gap flows, for example, in the Appalachians, which are nice to see. And then the cyclone is moving over the northeast. It's wrapping around the high intensity wind speed. So very similar actually in MPAS and the lens 2 hitting here the northeast. And then it's moving out into the Atlantic. So it looks like MPAS can do a pretty good job in downscaling this very coarse resolution data and produce realistic mesoscale structures. So this is how the same cyclone looks like at the 3 different meshes. So the left being the elliptical mesh, this is the most expensive one that we tested, the circular one, and the 62.3. So again, saying that the right one is 10 times more cheaper. And you can see very similar structures. Of course, there are differences, and they are partly because of exponential error growth, but also partly because of the mesh. But overall, the structures look very similar. And the third surprise for me, one of the major concerns I had when we started this, is that we will downscale cyclones that look very similar, independent on which case we downscale, because you start with a very low resolution model. But this is actually not the case. If you look at this example, here's a different cyclone. You can see a much bigger system. The center is now over the US and very high wind speeds here. And again, you can see the 3 different meshes producing very similar results. This is a cyclone that probably has tropical origins. So much smaller system, similar again between the 3 different grid spacings. Another example, just showing you the large variety of cyclones that you can simulate this way. So what the next steps will be, since this is quite affordable, like we decided to go with the 60-3 kilometer mesh. This allows us to downscale a large number of cyclones. So the goal here is really to do 200 cases in each climate period. We select 3 of those, current, mid-century, and then end of century. Downscaling this 10-member ensemble, this will hopefully allow us to get to very rare events to look at how climate change impacts extreme winds. And then also trying to analyze the structural changes to the cyclones, since we expect that climate change will also probably do something structurally to the cyclones itself. And in a follow-up project, looking at storm surge changes and extreme precipitation changes. But just to sum up, surprisingly, Lens 2 is doing a really good job. These climate models, this one that we developed here at NCAR, is doing a really good job in simulating extratropical cyclones and their tracks that go through the Northeast. MPAS can downscale these cyclones very efficiently with the 60-3 kilometer mesh very quickly. So as showed the 30-minute runtime, and create very realistic looking mesoscale structures. And these different cyclones really look very differently concerning the structure. So this is giving me a lot of hope that we get a large variety of different cyclones and can really assess how these kind of cyclones are changing into the future climate. If you're interested to look at this data set as well, this is an open data set. Please reach out to me, and I'm happy to take any questions.
We have lots of time for questions. Any questions in the room or online?
How important is it to have the sub-daily output? Would you be able to work with the daily output of the larger number of members?
It's completely unimportant because we run the global MPAS, so we only need initial conditions. The problem is that the daily like the other ensemble members don't have 3D output. So now you cannot initialize. But that's the problem. But if you would have at least one time step per day 3D data from the others, you could do the downscaling as well.
Hi, great talk. You mentioned that in future work, you might be thinking about how structurally the storm would be changing in future climates. I was wondering if you had any preliminary thoughts about that.
I can show you, like this is in one of the follow-on slides. Let me go there. Like what we looked at is, at least in the large ensemble, in the climate model, how the tracks might change. And what you see is that in the future climate, this is on the right-hand side, these are the annual maximum cyclones. So these are very intense cyclones already. What you basically see is that we have reductions in the cyclones that come from the tropics and also more from Canada, but we have an increase in cyclones that track through the southeast. What this means for the cyclone itself will be, we have to see, but it probably picks up a lot of moisture. So maybe diabatic processes will be more important in the future in these cyclones. And what we also see, this is the next plot, in the lens 2 at least, we see a clear increase in extreme wind speed. So this is shown here as return values over, this is the first model level wind speed, and you can clearly see the beginning of the 20th century, they were lower compared to current mid-century, and then the end of century are quite higher wind speeds in the climate model. So seeing how the downscaling is doing there will be interesting as well.
Just to give you maybe a look on the West Coast, we did this. We downscaled CMIP5, down to 12 kilometers using WRF, and there was virtually no change in the intensity of the cyclones, the winds, or the tracks. So on the West Coast, global warming had very little impact on mid-latitude cyclones. The answer might be different place, but something to keep in mind.
Yeah, I should look at your publication, Cliff. Yeah, thanks for letting me know.
So as a civil engineer, I appreciate your study for sure. But of course, as you sort of said in the beginning, it's the water on the coast that kills and damages more than the wind does. And so focusing on the track and the maximum wind speed sort of puts under the rug the fact that forward velocity, size, wave and storm surge generation in general, but particularly the size and forward speed have an impact on surge pretty significantly in the first order. Did you look at that at all?
So since we didn't look at, like, we don't have any future downscale simulations yet, and I didn't look at this in the climate data, but this is our hypothesis actually, that the cyclones will track slower and become bigger. If this really turns out to be the case, this will be interesting. But just an anecdote, like we started off thinking we want to do storm surge. This is an insurance sponsored project and they don't cover storm surge. So we now are looking at extreme wind speed and we'll do the storm surge modeling afterwards. But that's definitely on our mind.
Yeah, but there are three, not just the intensity itself, the forward speed and the size are incredibly important for the other tubes.
Yeah.
Yeah,
thanks.
Like I said, civil engineer, I really appreciate what you're doing anyhow.
Yeah, thank you for the comment.
Hi, nice talk. Do you have any plan to run tropical cyclones? Okay. We have recently seen the cyclones are getting longer time over the land, and any future prediction of the intensity or the wind speed in the future cases, that would be useful, particularly for the Bay of Bengal. We are facing cyclone almost every season.
Yeah, no, good question. So we will include tropical systems here. And again, there's some studies that suggest that the tropical systems might reach higher latitudes into the future. So some of these storms will likely be tropical. It's a small subset, but probably most of them, I guess, will be extratropical. But we try to include tropical as well.
Thanks.
All right, thank you.
Thank you.
Our next speaker, Mei Wong, will tell us about the impact of upstream errors on the medium range predictability of convection permitting forecasts.
I know how to use this. All right. Hi, everyone. Thank you. My name is May, and today I'll be talking about some of our work on looking at medium range convection permitting forecasts, and especially looking at upstream errors. So on the first day of this workshop, we've heard several talks looking at the application of global variable resolution convection permitting forecast, and even in the previous talk also in downscaling. Traditionally, convection permitting forecasts are typically run using a regional model, as you all know, for example, using WRF. But with the development of global non-hydrostatic atmospheric models, especially with the variable resolution capability in MPAS, it allows us to eliminate the need to impose lateral boundary conditions and dependence on an external driving model. So here we wanted to understand using this new model development of MPAS and its capabilities of running variable resolution, how can we use it to better capture the atmospheric processes needed to improve predictability, especially for applications such as medium range for convective scale forecasting? So the period of interest that we're that we have is the May 2019 multi-day tornado outbreak event. We're focusing on this period because, well, specifically, Gensini et al. 2019 has highlighted this period as being a forecast of opportunity using MJO related indices, and they were able to actually detect enhanced tornado activity up to 4 weeks in advance. So we're not suggesting that we're going to look into these forecasts in terms of predicting tornado outbreak into the details using MPAS simulations, but this does give us a particular interest. Specifically for this period, there were over 300 tornadoes spotted, as well as 7 fatalities that were reported because of this outbreak. On the right here later on, Miller et al. 2020 did a really nice comprehensive study looking at 30 years worth of tornado outbreak events in May over the US. And then they did a cluster analysis and identified 5 dominant weather regimes. And this is the pattern that they identified for the May 2019 period. So here we have the an upper level trough on the west side of the US, and then with a thermal ridge to the east, really supporting that southwesterly flow, providing that boundary layer moisture and heat that was needed to support that convective outbreak. Here's another figure from that same study, Miller et al. 2020. In the x-axis, we have the 30-year period, and in the y-axis is the day of the month in May. So you can see in the far right column here, it's showing it pretty clearly. The far right column is the May 2019 period, and you can see that there's 2 distinct tornado outbreak events. One that happened around May 9th that's more short-lived, and then in the latter half of the month, you can see the really persistent weather pattern that lasted for almost the whole second half of that month. So it is having this persistent weather pattern, meaning the weather regime. We're interested to see if MPAS is able to detect this in medium range, so like in 7-day forecasts. So the set of experiments that we're looking at is using the global MPAS variable resolution 15 to 3 kilometer mesh with the refinement mesh over CONUS and then 15 kilometer elsewhere. We used version 7.3 with hotfixes from version 8 because we know there were issues with input to the cumulus scheme. And also we implemented new online potential vorticity diagnostics. We ran 10-member 7-day forecast initialized daily at 0 UTC using GEF's initial perturbations for the entire month of May 2019 from May 1st to 31st. To save output storage space, we output only 3 hourly 3-dimensional output at 28 isobaric levels, and also hourly output of other 2D diagnostics like precipitation, CAPE, etc. And the physics suite that we use is the convection-permitting physics suite, but using the scale-aware Nutica scheme. And I just wanted to say, if you're interested in the online potential vorticity diagnostics, hopefully you had a chance to stop by Amanda Chastain's poster yesterday. But if not, here is a link to the manuscript describing this potential vorticity diagnostic package that we recently submitted. So here's a first look of how MPAS did for this period. This is the domain average MPAS precipitation forecast over the east of the Rockies. And the black line is MRMS, so our observations. And then the orange line shows the range of MPAS forecast from the 10 members. And you can see that actually MPAS did pretty well. There's some spin up in the beginning, as some of the talks described also on the first day. But it's around day 6 and 7 that we start to see this under bias kind of crop up towards these later lead times. So I know there's a lot of plots here, but I'll kind of run through it a little bit. On the left here, we have basically the same MRMS precipitation observations, but now we kind of expand it and look at it in more details. So in the y-axis here, we have too slow. On the left figure here on the y-axis, we have forecast hours, so running from 0 to 168 hours, so day 1 to 7. And the x-axis is the initialization day of May 2019. So if you run, go up the plot vertically, you're looking at sort of, I guess, the valid time of the increasing forecast lead time for the forecast, but this is observations. In the diagonal, in those gray dash lines, is a representative of the same valid time. So in the MRMS plot, you'll see exactly the same data being plotted in the diagonal because they're valid at the same time. On the right here is what MPAS says in terms of precipitation forecast, again, average over east of the Rockies. You can see that in general, MPAS actually did pretty well. It captured that May 9th event and the multi-day tornado outbreak in terms of the precipitation pretty well as well. They all seem to agree closely. Of course, there's differences because they have different initial perturbations. But if you look a little closer, you'll see that it is certainly especially in the multi-day tornado outbreak event between May 17th to 23rd, towards say day 6 and 7, that's when we start to see these precipitation biases kind of pop up. So the next thing we looked at is looking at the large scale errors between 30 degrees and 70 degrees north. Again, averaging over CONUS. This is now large scale using 200 hectopascal Heights RMSE. And kind of peculiar that you can see that same sort of bias crop up around the same time. So I can go back and you can see this precipitation bias that appears for that severe outbreak event. And then the bias is showing up over CONUS there as well. If you look further upstream into the Western Pacific and Eastern Pacific, you can, first of all, you can see that the errors are certainly flow dependent and depends on the regime of that day because they kind of flow more diagonally along those gray dash lines. And now you focus on the rectangles that I kind of put on there. Those are just highlighting the sets of forecasts. And you follow them upwards, you're basically going through the same sets of forecasts, but progressing in forecast lead time. And you kind of see that blob of bias, of RMSE blob, appear to propagate from the Western Pacific into the Eastern Pacific, and then ending up in CONUS during that tornado outbreak event at day 6-7. So if we look at the average RMSE of this large-scale bias averaging over all of our forecasts, this is what we get. The top plot shows RMSE and the bottom shows bias, and the y-axis shows the sector. So by sector, I mean I just basically looked at the between 30 degrees and 70 degrees north latitudinal band and then cut them up into little longitudinal chunks. And then the errors is plotted. The errors clearly show that a lot of these biases are originating from the Western Pacific and also growing a lot faster than other regions, indicating, again, maybe some signal of its propagation into the CONUS region. And also kind of peculiar here is that when you look at the CONUS region, maybe hard to see the numbers, but there's a dip in the RMSE and also definitely a reduction in the biases over the CONUS, which could be, remember, the CONUS is at 3-kilometer mesh spacing, so it could be an effect of the increase in model resolution, but certainly needs to be investigated further. So now this is just looking at one particular forecast. So the May 15th initialization. I picked May 15th because May 22nd, which would be the day 7 forecast, is one of the days that had the lowest predictability during that tornado outbreak event. And if you look at this plot on the left here, this is kind of like a Hofmöller diagram of the ensemble bias of 200 hectopascal height, that you can certainly see signals of error propagation originating from the Western Pacific and propagating into the CONUS region, where the Rockies is highlighted with that green dash line there. And on the right here, I'm just showing day 2 average biases and day 3 and 4. So you can, even at day 2, you can start to see over Central Pacific and maybe a little blip on in the Western Pacific region where the biases start to grow. And certainly it kind of amplifies along that North Pacific jet here and eventually propagates into the CONUS. Of course, that was looking at one specific forecast. If I look at the biases of day 1, 4, 5, and 7 averaged over that whole tornado outbreak event, you can kind of see that signal again pretty clearly of how the central, there's a bias blob there, negative height bias over the Central Pacific and a smaller bias over the Western Pacific. This really starts to grow and amplify much faster. So the last thing I wanted to show is the propagation of convection upstream during this period. And this was sort of highlighted as one of the mechanisms in Gensini et al. 2019 as being one of the contributors to the wave breaking that eventually happens over Western Pacific and leading to the synoptic setup for this tornado outbreak event. So on the left here, I have the I-merge precipitation field. Sector 4 is, as a reminder, that's Western Pacific. Sector 5 is the Central Pacific region, and Sector 6 is over CONUS. So you can really clearly see that propagation of convection know how to use this, convection really propagating into the CONUS region during this period of the tornado outbreak event. And on the right here, I'm just showing day 2, 5, and 7 MPAS, one of the member precipitation. We definitely need to dive deeper into this in terms of verification of the precipitation upstream. But what I'm trying to say here is that convection upstream can certainly modulate the large scale environment, which can then propagate and impact the medium range prediction skill over CONUS. So this is sort of my forward-looking slide of what's next. Certainly, I think we can use MPAS, variable resolution mesh, to dive deeper into the atmospheric processes and in terms of the errors that needed to improve predictability, especially for medium range convective scale forecasting applications. One of the first things, so almost like a low-hanging fruit, is to increase the model resolution upstream. Not to suggest that this should be done for operational purposes, but certainly something that we could use to examine processes upstream and representation, especially of that convection that was propagating across the Central Pacific. The second thing that we also will do, given our potential vorticity budget diagnostics, is to use them to understand better the diabatic heating and the impact on large-scale circulation, so looking into the model scale error propagation pathways. The third thing is to, obviously, there might also be model physics errors that are occurring upstream over the Pacific, over the tropics for sure. So another thing that we can do, and I am in the process of doing, is to diagnose sources of fast model physics error in upstream regions, such as over the tropics or Pacific, using its for example, a data assimilation system, because in the past, studies have shown that using short forecasts, you can really highlight actually forecast errors that accumulate into these longer range forecasts. And then with the cycling system, you can routinely compare against observations and be able to use other diagnostic such as tendency to diagnose the sources of these model physics error. Of course, this was just one case. We should do more cases. And I think the Miller et al. 2020 was a really great database of all these cases, especially with the associated weather regime pattern. So looking into similar cases with similar weather regime type would be really interesting. So I'll also add that this expanded 15 to 3 kilometer mesh is in progress. The generation is in progress, but as you might know, it takes a while. So thank you, Michael Duda, in advance. I know it's a hard task and challenging task, but thank you.
We have any questions? Going to run this expanded mesh. Have you considered just running the 15 kilometer global?
15 kilometer global? I think we,
would that potentially be informative to some of the issues you're trying to address in terms of the error, reduced error over CONUS?
Did you say 15 kilometer global?
Yeah, if you were in 15 kilometer global, you'd have course everywhere. And perhaps the errors over CONUS would be larger and more consistent with the errors in the 15 kilometer regions that you showed. And it would be cheap.
Maybe, yeah. Maybe we should talk a little bit more about that after. Thank you.
Well, the solid blue curve there on that figure, is that a proposed high resolution region?
Oh, sorry. Yeah, the legend's gone. The blue curve should indicate the 15 kilometer kind of region. Anything outside of that, it looks really strange because of the projection, but it's actually an ellipse.
Okay.
Yeah.
It's just interesting it dives so far into the southern hemisphere, but it basically excludes the Middle East.
Right. Yeah. The, I guess, intent of this is you could play with it. You could rotate it. You could play with it. And what I'm trying to really capture is the almost the maritime continents and kind of over the Central Pacific, Northern Pacific, that region there. So, yeah.
Okay, thank you. So our final speaker for this session, Lou Wicker, will tell us about idealized squall lines in WRF and MPAS.
Okay, great. best for last, I'm sure. So, is there a spotlight here? Oh, okay. So I'm just this is sort of follow up. Some of you are probably going to see some slides you've seen before, or think you've seen before. But I've kind of gotten interested in how we're going to figure out when you have a model that's working at least close to what the current state of the art models are. And some of you have seen this before when I was trying to understand the operational characteristics or the operational biases we've seen in the RRFS through using the FE3 die core. And basically what we found there was that there were some biases due to the intense updrafts that FE3 tends to generate, especially in low shear. So I've had to set up all these this framework over the last year or two to look at this. And it's probably hard to see in this now that I see it. I have a new motivation for trying to understand this problem, which is that we're trying to produce a WRF's MPAS WRF's big brother to WRF MPAS, WRF WRFs, which is the Warn-On Forecast system. And so we're tuning up this new system, and it may be kind of hard to see here, but there's a whole bunch of spurious cells down here, kind of widely scattered in this. This is basically about as best we could get for this case, and also off the coast down in here for this April case that we're just using as a test relative to our WRF WRF system. So this is MPAS WRFs, this is this, and these are these paintballs, and the dark spots are actually the observations from MRMS. So we're trying to understand, why is it noisier? What's going on here? So, I mean, part of the challenge, I think, or the part of the things we've learned is over the last 7 or 8 years, pretty much the hard way, is that we don't really have, I think, a good unified set of tests for convective scale modeling, whether it be idealized, I think we do, but for the real data cases. But it turns out you can learn a lot about what's going on in these sort of new cores and maybe new numerics by just looking even at idealized things. Obviously, we want to compare things to observations, but we don't have a lot of really detailed observations at storm scale. So I think we can still do a lot of good research and actually evaluation by looking at sort of compare model to model for certain situations. So the real question is, how are we going to robustly test convective storm behavior? And I would argue that the best way to do this is to use simulations of squall lines. And I think we should do it in the idealized sense, although you could obviously do real data cases. But I want to take out the physics, and I want to take out the initial conditions, and I want to take out the boundary conditions. And I want to look at least at, in my interest for many, many years has been in dynamical cores and how this works. So the previous work that I indicated in the last page had some references, for example, to Ulrich and the DC MIP tests of the supercell. But with a supercell test in a global model, that was done with a global model, you don't really get many cells, right? You get a supercell. Maybe you get a split. So I think that what's much more interesting to look at, because you get a better statistical sample of behavior, is to look at squall lines. Squall lines are also a very common type of phenomenon. So if you can do squall lines well, you're probably, or at least in the ballpark with your squall lines, you're probably in ballpark for a large spectrum of convection. And as I said, that if you do a simple squall line simulation, a large enough domain, you can run it for 5 or 6 hours. You can get a large number of samples from your individual cells, you get a lot of good statistics, and it's pretty easy to sort of set up the environments. So this is kind of what I did, and now I've been trying to look more at MPAS, because MPAS is not behaving like WRF in our rapid cycling DA system. It's not terribly different, but it's not quite the same. So I took WRF MPAS, and I'm including CM1 here. And I basically I'm running Kessler microphysics, because I actually know what the code is in each model, and it looks the same. I'm running 3 kilometer horizontal, which is pretty marginal resolution, but I'm just starting to do what just trying to emulate what the CAM situation is. 60 vertical levels. Because in the real data cases, vertical mixing is done by the PPL scheme. I've tried to disable that as much as possible in the nameless parameters. And I want to emphasize that the other settings for the first part of this talk are out of the box. And what I mean out of the box is sort of the defaults, or at least the defaults that I run them and how we run them down in SSL. So this fifth order transport, this will become important in a few minutes, and for both the CM5 and WRF. And there's no explicit horizontal filtering enabled in the initial settings, but in MPAS, the default is this sort of it's not fourth order transport, it's sort of 3 3/4 order transport, but I'm just going to call it fourth for convenience here. There's some filtering done in horizontal using two-dimensional Smagorinsky that's also done in WRF as well. And then I'm just going to basically set up a couple of environments with some soundings that have some instabilities. They have the same RH. That's the advantage of using the McCall, and a couple of shears. And we're just really going to look at the 6 meter per second shear, which I call kind of low shear, and a high shear. And then I basically start a 300 kilometer domain on 300 square kilometer domain. And I basically put 7 bubbles in the west part of the domain, and off we go in the usual sense. Now, some of this talk is going to look at storm objects. And basically, this is a methodology that we use a lot for basically looking at convective scale, especially for our warn-on forecast system. So if you hear me talking about updraft profiles from our storm objects, what we've done is we've looked where the composite reflectivity is greater than 35 dBz, and the vertical velocity is greater than 5 meters per second at 700 millibars. And we basically then identify these objects with this mask and then basically average vertically, which isn't perfect in a squall line, right? You have some tilt, but we average vertically in these objects to get some things like size and shape. And I'm basically going to show you some vertical profiles of W, and then I'll show you some other two-dimensional fields. So this is what the squall line looks like for the low shear case with the lower cape. CM5 is on the left, WRF in the middle, MPAS-4 on the right. There's some mix up in the colors, but the regular MPAS-4 will be red. So what you have here, and I don't want to do that. There we go. I put the cold pool down here, which is just sort of shaded. I don't know if this is coming. Yeah, it's coming through better up there than on here. And then the blue areas or the objects in here are basically where the updraft is bigger than 1 meter per second down low. So you see the gust front, you see some rearward convection. This is a funky thing. And they have differences, right? WRF and CM5 are somewhat different, but what I want to sort of focus in on here is the fact that out of these two look qualitatively similar after 4 hours, same time step, same microphysics, all that stuff, but MPAS is different. MPAS-4 has a much larger cold pool, and the convection and the convection, if you will, is extended rearward the backside of the cold pool. The domain is doubly periodic, so you may start seeing this poke in, but this is just a subset of domain. So you see about the same location horizontally, but definitely an the Y direction here is much larger. What's interesting, if you look at the updrafts, and I've seen this pattern before, is that while the storm structure is larger, it's probably weaker. And you can actually tell this by, obviously, this is the vertical velocity profiles for 3 experiments. In the weaker shear cases, that's the WRF and CM1 are not identical, but very much more similar than MPAS-4 is. And what I wanted to point out was these counts up here. These are the numbers of objects. And if you look, MPAS always has in these things, more objects. This is almost twice as much. This is about 50% more. This one, because of the strong shear, and that's where you see it match better, it's not quite as much different, although it's a lot, both WRF and them have many more objects than CM1. So the strong shear tends to, when we run strong shear cases, what I find with this is it tends to mask the differences in the cores and how the system's behaving. So the weak shear cases, which is where we sort of found some issues with the RRFS, is actually kind of more illuminating about the different behavior characteristics. Now, this is the kernel density estimate of the accumulated precip points, and you're going to see the same type pattern. There's WRF and CM1 are pretty similar. If you go to this stronger cape here, you're going to see they're very identical, but the MPAS sort of has this big hump down low with a lot of density down in this very small amounts, and then it sort of tails off. And then as you go up in shear, it gets closer. And if you look at precip, you'll see exactly what you expect if you've looked at this long enough, is that the WRF and CM1 and these precip, horizontal 4-hour precips, are about the same in extent. There's obviously differences. That's the shading. There's some updrafts drawn on here, but MPAS is much different. It's much bigger and wider in the cold pool. So what's going on here? Well, what I think is going on is the transport is mostly weakly dissipative in the fourth order scheme. And this is what that would look like in a sort of simple advection test that's very common versus the third order transport scheme, which is more damped. It's not totally different, but it's enough in this model. And I'll convince you by that by now going and turning on the third order advection, which is much more dissipative. It's more dissipation than really the fifth order is in CM1 or WRF. But the point here is that now we've recovered the sort of scale of the cold pool that's similar to the WRF and CM5, CM1. And it's basically now the structure of the updrafts are closer, they're fatter because this is a lower order scheme, which doesn't have as much resolving power. But you see these are fatter and it's closer to the front edge, much more like WRF and CM5. And if you go in and do the RBF, the KDE estimate, all of a sudden now you see that the precip for the third order MPAS transport, it sort of flipped over to the other side, but it's much more similar now in terms of than the WRF and CM1. So by changing the sort of dominant characteristic of the transport, you end up with solutions that look a lot more like what you were getting from sort of the standard community models. And these effects are associated with the weaker shears, not the strong shears. And just to prove that point a little farther, here's the MPAS-3 on the left. And you can see this starts to look a lot more like WRF in the simulation. CM5 is a little bit different at all, but that's a good thing, right? And to convince you even more, here is I ran CM1 and WRF with fourth order advection, and they have the huge scale just like MPAS-4 did. So you really do see the effects of the sort of leading order dissipation or dispersive of the transport. So it's something to think about when we're testing models and how to expect them to behave. And this is just the original stuff down here. So summary. So I think this has been a useful exercise and I'm planning to get this together. And then we're doing 3-kilometer resolution, which is really, really poor resolution for these things. I have done 1-kilometer simulations before, plan to do them again. The dissipation levels in the transport seem to account for much of the differences. And I'm planning to try to push this to GMD as a sort of benchmark set of runs for people to look at if they're doing other CAM development. And so I think what we've sort of learned to summarize here is that when we started doing the WRF's MPAS, we had such good success with the CAM using MPAS that we just assumed we could drop MPAS into our WRF system and get it going. But it turned out that when we sort of turned on all the bells and whistles of a rapid cycling DA, a lot of these differences, fundamental transport differences, started to sort of rear their head in terms of spurious storms. And so we had to sort of go back and think about this more. Of course, we're doing it in a fully cycled TA system. It's not the cheapest way to do it. But, and Daisy says, thank you for your attention. Thanks a lot, everybody. So. Uh-oh. Ruh-roh.
Here comes trouble. Just wondering, have you also looked at the differences in cold pool strength being produced? Because certainly if you produce bigger cold pools as opposed to differences in updraft structure, that could also produce the kinds of changes I think you're seeing, possibly.
Yeah, I mean, I did sort of, in those diagrams, they had like a percentage of the area of the domain that's covered by a -1 degree C or better. And I think the other thing I would like to do with this kind of stuff is actually look at where like the crossover between supercellular versus sort of multicellular behavior is do those those numerics and things actually change where your set points are in your solution space. But the short answer is kind of no. It was Manda.
Oh,
Manda.
sorry, go ahead.
Thanks, sorry. So is this explanation for why Adam said that the updraft helicity climatology was so much lower in MPAS compared to WRF?
No. Next question. No, this was actually what surprised us because we had such almost seamless results once we figured out a few of our stupid bugs with running the cams for the next day problem. So I think there's, I mean, the fact of the matter is MPAS is built with lower order differencing, which is either going to, it's not as, but you gain that in the horizontal. I actually think what we ought to be doing first is putting in a little better vertical transport because that doesn't cost you anything in MPAS because of the K index is the same. And so you could go to fifth order and vertical. We went to fifth order and the vertical in the HER and in some things because we really wanted to preserve the structure of some of the inversion layers and the cap and things like that. So I don't have a clear understanding why on a cam scale and next day problem it would be like that, but that could be a possibility.
I'll plead ignorance or stupidity or both on this. Is MPAS fifth order differencing not available for a particular reason technically, or curious what? Obviously you're making a case
it's all
for that.
Bill's fault. No, I actually want to put it in,
Right.
but I will tell you that there is a complication. We can do fifth order in the vertical. I want to put it in the horizontal, Bill. You're just gonna have to deal with it. But the problem is that very simply, because of the variable mesh grid, you can't just sit there and go, I'm going to get the neighbor over here and the neighbor over here and the neighbor over here to do your finite volume. So if you have a regular grid, like we would probably want to run over CONUS, we may be able to sort of put in some code that will actually do that, at least for testing. But when you want to generalize that to the whole globe and be able to do these other things, yeah, I know he doesn't want to see there's a fork right there in the GitHub. But if there's anyway, the short answer is I think we should work on improving the vertical because it's cheap, it's easy, it takes almost no coding effort, and then look at the horizontals again. But technically, you just increase the halo size. Right now, it's only 2, so you can only go to a 5-point stencil.
I have it in my contract. I get the last word.
Okay.
So what really pops out at me between MPAS-4 and the others is the presence or absence of convective cells on the down shear edge of the cold pool. So it would be interesting to see why that is. Is there a difference in the depth of the cold pool, for example, or is that just a place where noise is particularly likely to happen?
Yeah, I mean, some of it is probably just thresholding too, right? You're talking on the leading edge and things like that.
The back edge.
Oh, the back edge, yeah.
edge.
Yeah, I think, like I said, when we went back to 3, the structure was a little bit, at least more similar to WRF in that, but I have not looked at
And
the
that's
depth
what
of the
disappeared too.
Yeah.
A lot of it.
Yeah. So.
One thing is we don't know in these idealized cases which one's right? We don't
No.
have a solution
No.
to generate that. And in your motivation, are we trying to tune MPAS so it'll play well with a system that's been tuned for more distributive models?
So I think this exercise is about understanding the characteristics of the code relative to the other models. Okay. And I think that I'm not really interested in WRFing my MPAS, right? I mean, there's advantages to the MPAS that WRF doesn't have. For example, these are 3-kilometer meshes, but they're actually 16% denser. There's 16% more nodes in the same area for this thing. So you're getting better transport and things like that, which is one of the reasons why you guys didn't worry about going out to a wider stencil, because you have this extra degree of symmetry in the hexagon that you don't have in the quadrilateral. So the question in my mind is, what if you're looking at precip, you're looking at biases, for example. You have a precip bias and it's different from your current operational model. Where should you be looking for all of that? And that goes back to physics as well in that, but you can see that there's differences in precipitation biases or just differences in precipitation just from your transport and has a big impact. So I think you could actually ask yourself, is my bias because of my physics, or is my bias because I have a slightly different system that I'm working with?
Okay, let's thank all the speakers from the session. Hey, sure. Wait, Kelly, do you want, shall we begin? Okay, welcome back, everybody. The ice cream break at this WRF MPAS workshop is my favorite part of the week. And it lasts way too short a time. So I got a couple of things to begin. Michael Duda tells me that we are very, very close to the version 8.2 release. He's working on the release notes, which means the code and the repository and stuff are all set. So hopefully you may see that very, very soon. If not by the end of the week, because a few people have to sign off on the release notes, certainly by the beginning of next week. So that's going to happen. And so all the things you've heard about coming out in that release will be there. The second thing, most of you were here yesterday during the discussion in the afternoon. There was a very brief discussion that followed the presentations on chemistry. It was very brief, and that it spent maybe about 15 minutes, but there was an awful lot said, and maybe the briefness of the slot, people got right to the point. But I thought I'd like to give my brief and certainly probably lacking in some subtlety summary of that, and see if anyone else wanted to say anything else at this point. And my understanding of what happened, because I'm not a chemist and I've never run WRF Chem or anything like that, but I work with those folks, is that while everybody loves WRF Chem, the major organizations that are behind it, most notably NOAA, but also NCAR and ACOM and NCAR, we have not been able to find resources to support it at the level we have been. So essentially it's out there, and some things may still come in, but it's difficult to see any major development on it and major support for that matter. So in MPAS, which is where we're shifting our development effort internally at NCAR, we have seen from presentations here this week that we're going to see a release of MPAS with CMAC. I don't know if we call it CMAC MPAS or MPAS CMAC, but I can live with either one. But that will be there. Okay, very good. It's fine with me. And so I think that will certainly potentially work for some of the applications we've been hearing about. But alternatively, there's also development within ACOM on their Musica system and the model independent chemistry module. I think I have that acronym right, MICM. And there's some NOAA support to bring MICM into the UFS, I think, using the CCPP, I believe, which we can likely leverage for MPAS also. So kind of bringing these groups together and seeing that happen. Continuing on the question of support, though, we are leveraging not only resources in NCAR, but also participation and support from a number of groups in the community to see that happen. But as such, the support level is not such that anybody's comfortable saying when that may become available. And that's something I think we're going to need to have to try to address, kind of longer term support for that effort, so we can set milestones so that the community, all of you that use those kinds of tools, will have a sense of when they'll become available. I mean, this is something we really need to address. If anything, looking back at the days of WRF, the chemistry community is just huge, and we have to start looking at that. I can tell you, it's just another aspect of that. I have one paper with, well, more than one, but one particular paper to chemists. It's George's paper describing WRF Chem, and he was generous enough to put me on as an author because we discussed a few things with transport or something. And that is my most highly cited paper by far. It's just crazy, which just says how many people use WRF Chem and reference that paper and how big that community is. So we're well aware that that's something we need to address, and we're trying. Yeah. And what would be more fitting, right? Yeah, this was, yes. And thank you. Yeah, that was good. So does anybody have anything else they want to say about chemistry, given how short that session was yesterday? And was there something that maybe should have been discussed that we didn't have a chance? Okay. If you think of something in the rest of this discussion, you can just pipe up and say, going back to chemistry, if you really want to. All right, so I have just a few slides. This was actually a slide I had for yesterday in case we ran out of things to talk about. Of course, we didn't, or Tuesday, I'm sorry. And these questions came, I asked Kate Fossel, who's working with us at NCAR, with interagency issues and stuff, for a list of questions. He sent me an email, and the questions were so good, I just cut and paste them out of the email into this. So thank you, Kate, if you're out there, because she's not here in person. So essentially, these are questions about what, I just want to open it up. What would you like to see? And the earlier discussion session, even the chemistry one more so, or at least as much too, we kind of heard a lot of views from the institutional perspectives, the big folks, NCAR, NOAA, other major centers like that, and not so much, for example, from those of you from universities who have students, et cetera. So I would very much encourage, what would you like to see? What would you like to potentially, what would prioritize, would help you transitioning, for example, from WRF to MPAS, things you don't have that you'd like to see? I know it's Thursday afternoon, and I'm not going to call on Cliff because he started things Tuesday. What would you like to see? Even though I know you don't live in a university teaching students anymore, but you work with some.
I teach every year for a week.
For a week. Okay. For a week.
I still, this is not going to surprise. I'm just trying to get the conversation started. Let's see, what can I say that would actually start a conversation? I would say gridding, how to generate grids, gridding there. Because I think that, does everybody think that that's one of the big impediments here? So there you have it. We can go drink beer now.
Okay, I have a response for that too. After this week, I'm going to prioritize, meaning I'm going to try to do it, but maybe you and I can both work on it. Is using the projections that we use, for example, WRF for limited area, and take perfect hexagons and just use those projections to map them to the sphere. That's a relatively straightforward thing to do. I think between the two of us, we can probably make some progress on that pretty quickly. And Michael will show us how awful our code looks, but he'll be happy to clean it up for us, and maybe we can do that. So I think that's low-hanging fruit, and has really been for us. Hasn't come up in the triage list, but hearing this yet again this year, we heard some of that last year. Taking that to heart, and we're going to get that done. And that'll at least provide one thing. Oh, wait, one more thing. So everybody knew that was Lou Wicker, right? One person, someone mentioned to me after Tuesday session that some of the folks here, maybe for the first time, don't know all us old timers whom we're speaking, or even some of the other younger folks. So if you want to say who you are, I'm Bill Scaremark, by the way. So, and go ahead.
Hi. So my name is Marta Gil, and I work for the industry. So I'm not a researcher. And what we do is we use WRF for downscaling reanalysis to understand how was the wind at some specific place in the past. Okay. So we use WRF in a very localized way. And everything I've seen here in MPAS is more about global or very big meshes. And I think that there's a use case for this kind of smaller regions of the world, or even wind farm regions, that also want to run simulations. And I think the meshes in this case are much easier to generate, and it's not so expensive. But for me, the problem is to know if these meshes are suitable in the physical sense, because I'm not a scientist and I can only check against results. So maybe some sort of tests that I could use the meshes I generate and see if theoretically they are sound would be helpful for us, the smaller users of small WRF, small MPAS simulations.
Do we have those kinds of tests for WRF? I know we have some, but mostly they're idealized. Is there a WRF analog you can point us to?
I think for WRF, what I understand is that there's a standard, like you have some domains and some basic rules of thumb of how big your domains can be, right? Yes. With MPAS, there's not a rule of thumb of how your meshes need to be, and you only have sample meshes that are huge for my purposes. Yes. We don't have thousands of cores to run things. I want to run this in a laptop. So I don't need, right. I need a completely different domain of meshes.
And on our mesh download page, you'll only find global meshes. So except there are some regional meshes on Cartesian planes, but they're not on the Earth. So if you're doing any real data, that they're just not useful. So part of this issue of a question about mesh generation that Lou brought up, and I answered that we want to map perfect hexagons to these projections, I think would address at least part of your need. And the other part is effectively kind of a best practices guide or document or something. I know most of the tricks, but they're not written down in anywhere. So this is something that maybe we also need to be thinking about.
Hi, I'm Rob Fovell. I'm an academic. I have been teaching the current version of my NWP class at University at Albany for about 10 years now. Had about 200 students go through it. It's required in the undergraduate curriculum. So we're way ahead of the AMS undergraduate guidelines. Let me give you a little background of that. When I started it was 100% WRF and 100% grads. Okay. I used the WRF single column model to demonstrate PBL schemes and how they vary from scheme to scheme. I used the WRF two-dimensional idealized squall line to demonstrate microphysics and how microphysics influences how convective activity organizes and whatever. And the students are impressed, as they should be, regarding the kind of variety you can get from the same initial conditions just by changing model physics. We talk about the theory of PBL schemes, how different microphysics schemes work and things like that. So I'm going to try to approach this in the standpoint that what would it take for me to transition my class from WRF to MPAS? I've included a week of MPAS in the class in the last 4 years. Last year, I actually included a week of UFS. So I'm exposing them to that, FB3 based BFS, and a week of GraphCast. So all of these things are going in there. I think that what I would need to squeeze WRF out and replace it with all of MPAS is I would need more computing resources than is current that I would need for the current, the same activity in WRF. And I just need more computing resources. What MPAS has been greatly facilitated by, last semester I used UX Array for the first time, which really helped to visualize things. And if you can't visualize it, you know, half the students aren't going to get it, right? So right. The whole purpose of this is to see weather and see how weather varies with assumptions, initial conditions, boundary conditions, physics, that kind of stuff. So I think that a single column model version of MPAS and an idealized two-dimensional version of MPAS would really help me to do the PBL and microphysics demonstrations. More physics availability, it has improved a lot, but more of the WRF physics available in MPAS, right? Because even if, you know, what I often do, if I have 20 students in the class, I create a class ensemble where each student is responsible for contributing a different configuration, okay? It's easy to do with microphysics and WRF. There's enough microphysics schemes, right? You might think there's too many, but it works for me. So, okay. So last semester I had 32 students. That was a little harder. I had to come up with some clever ways of augmenting the physics and WRF, but more physics in MPAS, single column model, 2D idealized, and further improved visualization. So that would help me.
Okay, that's a lot. But could where's I want to say Jimmy, or I'm wondering if the single column model work that's being done with the DTC and the CCPP, is that right? Where's Jimmy? Is he here? Could Louisa? Okay. Could someone address that? I'm not quite sure who should, or who's hands-on doing the work.
Yeah, the people that know DTC, Alicia's not here, yeah, there is a single column.
Can we leverage that, or do we need to put some other pieces of MPAS, like the vertical transport or something, in there for?
No, a single column model just needs forcing, and
just needs forcing.
They have test cases, and they're enhancing that number of test cases. They've got there's a standard for test cases now, global standard that they've adopted. So I think that's a route if you want to test physics against real data. It's not often the way the WRF single column model is used, I guess, but that's the other thing I'd say is 2D. I'm not sure there's any benefit to making an MPAS 2D when WRF 2D will do the same thing.
There is an MPAS 2D.
Is there?
Yes.
Okay, well, that's what
we're good.
I didn't know.
Oh, well, there is.
Not well known. Okay.
And there's a Squall line test case set up in it.
Okay.
When did 2012. It's okay. Don't worry about it. But we can talk later. I can show you where it is, and it probably needs a little better setup for your applications, but it's there and it works.
So Louisa Nance, I'm the director of the DTC. So I think following on with Jimmy, I think there is some work that would need to be done for certain types of things with the single column model that would be compatible with MPAS, but I mean, you wouldn't be starting from scratch. So, you know, that might be, especially with the direction everything's going with respect to the UFS and NOAA and stuff like that, that might be work that would be done, that might get funded. So,
and I think we're looking to leverage these efforts, and why build another single column model if one's out there that can use our physics and yes. Okay.
Kind of fun to be somewhat preempted, because I was going to talk about a very similar one. This is not just a question of the model, but the fact that we need to be sure that we get enough new young blood in modeling and in DA to begin with. And so along that same line of what I am Hendrik. I was the one who introduced himself on Tuesday. But Hendrik Tolman, I am the very civil engineer from NOAA. And so one of the things that Neil and I have been talking about, so Neil Jacobs, who is now at CPAS, and Alison Gregory, is a way to get more people interested is to make these kind of models as classroom tools. And it's not just a question of having a smart professor who can do that and can rub that off on their students, but it's also a question of how you release codes and make sure that you're able to run a high level model, but at low resolution, so that you can run it really quickly to show these kind of things. And so apparently we're thinking the same already. if you're talking about merging the MPAS and the UFS a little bit more, I'm pretty sure we need to talk between you folks and Neil and us about leveraging that kind of stuff too. In terms of being able to much more easy use these kind of tools in a classroom. And actually, I'm in September, I'm deliberately going to San Diego to work with the Ocean Discovery Institute, because I'm trying to figure out if we can actually do this even with middle schools and high schools.
Abraham. Thank you. Go ahead.
Okay. Hello. Yeah, I'll do a quick introduction since that's the new thing. Yeah, so I'm Abraham Roseman. I'm a second year PhD student and currently working on idealized convection initiation with CM1. But I'm very interested in regional modeling with MPAS. And so I just have a few comments. I think there's like 5 of them. But I think a lot of other people have said a few of these, so I'll just briefly go through them. But one is definitely the technical guide, getting that finished soon, because working with CM1, there is a smaller technical guide, but it's not as in-depth as the one that was introduced here. And I think it really helps when going through the model and making changes if you know the equations, and also just knowing how the model works. There's papers for MPAS I can look through, but it's more intuitive when it's organized well.
Are you interested in being a reviewer of that?
I could be, yeah. I can.
Okay. Okay.
Very organized person, I guess. Yeah. And yeah, the better like user selection, the grid generation. With CM1, since it's a Eulerian grid, you can just like in TNG all that, and it'll just do it for you. And that would be really nice to see in MPAS. I know it's really difficult working with this unstructured grid. Yeah, better support for idealized simulation like CM1 has. I think someone else already brought it up. Another thing that CM1 has, which is really nice, is you can change the order of advection. I think they even have like a 10th order, like Weno advection scheme in there. And again, that's pretty hard to make those operators for MPAS, but if that's available in the far future, it'll be very helpful for setting up these idealized simulations. And also, I recently became more used to using terminal and like SBatch, and like CMake is a bit new that I'm learning about, but I think it would be easier for people who don't really know how to use terminal very much, like I was recently, if there's some sort of like software, maybe like C++ or something that does everything for a user who's not as advanced. Or maybe some on-demand simulation packaged sort of.
Okay. So you've heard the comments about grid generation, and we're taking that to heart, believe me, and I'm going to move on certain things. In terms of the idealized configurations, we have a few, very few. However, our experience with WRF has been, those few are, there's enough information in there when you see how it's set up to extend those to other idealizations. So understand CM1 too was built for idealized simulations, whereas MPAS was built for the sphere and global, and we're going to those idealizations we developed that just for testing purposes, but that's there. If there's specific idealized configurations people would like to see, they should potentially go to the WRF MPAS forum and ask if anybody who has done that, because a lot of those idealizations, people that are who know how to do that in other models, oftentimes can come to MPAS and set those up themselves. So it may well be that some of the idealizations are already out there, and people are using them. They just haven't contributed them back where we can package them up for easy consumption by other users. So they may be out there. Or we could see that and I could say, oh, it'll take me an hour to set up something like that. And I can do that and push that over to you, for example. And if it looks like that's something that having it out there makes sense, we can then just package it up and put it out there in a release. Although a lot of the idealizations are not necessarily, for example, part of the GitHub release. We just put the ancillary data you may need, the meshes and the name list out there so people can access them. That's what you'll find, for example, for the Squall line that's out there and the supercell test case. So that is more knowing where things are. I think there were two more things you asked about that I forgot to write down. So
if you'd like to, you can talk, or you can go to someone else.
Yeah. So the tech note that's coming, and also the developer's guide, and that tech note I just showed a little piece of it, and but I would definitely like some people whom are users to be looking at it before we finalize it for sure. So we'll be going out for
you can email me.
Yeah,
you can email me about it. Yeah.
Okay. Well, I'm working on there's 3 main chapters on the numerics. So if you're comfortable looking at numerics, I'll send you those things. So, and I think we're hoping to have enough of a draft that we can maybe put it out there for people to start looking at maybe by the end of the year. So I think a lot of things are coming, and they're high on my priority list and the other developers too. So
thank you.
Thank you. I don't see any. Do we have any other comments?
Hello. So I also come from industry, and I totally agree with Marta that maybe one of the key points that we should take into account when thinking about transitioning into MPAS for us is computational cost. And I have never used MPAS yet, but so please correct me if I'm wrong, but as far as I could read, some kind of local time stepping is possible in MPAS Ocean, but it's not for MPAS-A. And I'm just curious if some kind of local time stepping that allows the user to use different time steps for different regions depending on the spatial resolution could be interesting. And could help to reduce the computational cost. And so many small institutions or companies don't have massive computational resources. So if mainly if it could help to reduce the computational cost, and at the same time to not modify so much the quality of the outputs, it could be a really interesting feature for many users, I think. I don't know if it's something that is written down in some to-do list. I don't know if it have some priority, or I don't know even if it does exist yet. So that's all.
2 points come to mind. One is that in side-by-side comparisons of WRF and MPAS, when they're configured similarly on regional meshes with similar cell spacing, the cost of WRF versus MPAS are effectively the same. Maybe a little bit different, but you wouldn't really notice it in practice. So most of the increased cost of MPAS is, I think, people running globally, but are only interested in certain regions. So one solution to that is to set up MPAS regionally like you would WRF. Now, if you're looking for variable resolution, so you want a bigger domain, but then you want to go down higher resolution where you would typically use nesting in WRF, you'd use the variable resolution in MPAS. If you introduce a way to change the time steps, then you're essentially introducing a temporal discontinuity in your integration. That may not be as significant as the step change in resolution of a nested WRF, but I think it may well be noticeable in some applications. We have chosen not to do that because it takes a lot of extra code to implement. There is someone who's done that with MPAS over in Asia somewhere, and they actually gave a talk here. I don't know if it was last year or pre-COVID, but it's been done, and claimed that it worked great. So they didn't offer it back to us. And I don't know what to say about that. Perhaps if we can look back at past workshops and find out where that is, and I can put you in touch if you're interested in looking at that. I do want to say, if you look back at WRF and how its capabilities grew, both idealized but more real data, all the physics, most of the work wasn't done here. It was done by the community. So we're really looking for people who want something, and those that have the capability to implement and bring it to the community. So yes. No, Lou, you're not next.
Short people problems again. I'm Tanya Spiro. I work for the U.S. Environmental Protection Agency. And unlike my colleagues who are here on this trip with me, I am not part of the MPAS-CMAC team. I actually use WRF for regional climate modeling. And so that sort of genre hasn't been brought up. So I will bring up a few things that are really impediments as I see them. First one is, I'm not really sure. I know there's regional MPAS. I saw a nice tutorial on that by Michael Duda, either last year or the year before, I can't remember. Right, made it sound very approachable. Still haven't tried it yet, but the whole thing about setting up the grids may be a little bit more daunting than I'm willing to take on. The second thing is one that I've already discussed with Bill, and I've discussed with a couple other folks, is we need some way to constrain the simulation towards a large scale model. And while there is a grid nudging capability that's in there, courtesy of Russ, we need something. We're typically using spectral nudging right now in WRF, and that doesn't make sense in MPAS, so we need something else. And that's not there. It just needs some sort of development. Third thing is that if we're going to change, we actually need to test it out. And we can't just say, hey, let's pick up MPAS, whatever form it is, pick up your favorite set of physics options. We are using some things that we had arrived at through systematic testing, some of which don't exist in MPAS. So that's a little bit more daunting. That's going to take time, and that's an impediment because it's making that kind of change is an investment we can't do just yet. The fourth thing, which I'm going to date myself here, I've been part of this community for more than 30 years. I know Fortran. I know it really well. The world doesn't have a need for a few good Fortran programmers, but I don't know Python, and everybody knows Python. And there's a learning curve. If you're going to keep switching things over to using Python, old-time people like me are not going to be that fast to jump to it. So the fifth thing, and I'll end with this, is a little bit more sensitive, but I did say I work for the EPA. We are wagged by political elections. So timing is everything. This is just not the time to invest in something like this yet. But thank you.
I can empathize with your Fortran thing. I do know a little bit of Python, but it's kind of a little bit. Yes, in terms of the nudging capability. For those of you who remember WRF and transitioning from MM5, nudging was the critical stumbling block to get certain major users and developers to move. Thing about spectral nudging is that we don't have a nice grid. We have an unstructured mesh. So it doesn't make spectral techniques all that, they're much harder to deal with. we've discussed, and actually I can say that we're looking at wavelets because there's natural wavelet decompositions for MPAS meshes, for SCBTs. And that may be a path to clean nudging that takes advantage that can directly use the MPAS mesh, where you're not doing interpolations to yet another and then interpolations back when you set your nudgings up. It would be just on that mesh. So I think there's some good possibilities there, and there's a couple folks at NCAR working on it for the high resolution applications to nudge back to, for example, GFS. So I think we've got some possibilities there that are slowly evolving, and I'm hoping at next year's WRF MPAS workshop that we'll actually see a presentation on that, because I'm actually really excited about that work. Regression testing in MPAS. We don't really have a good system or any real system, which is a problem, an automatic system. We need that. We are in the process of overhauling in part what we use for WRF so that we can lessen our support burden there, which isn't too great, but it's right now, but we need a better system, and we're going to then implement something for MPAS based upon what we developed for WRF. So that's moving, but it's moving more slowly than I think we'd like. Yes, okay. I'm not sure if I should address anything else. Thank you, but for those comments. You've been standing longer, and then Lou, you'll get your chance.
So Caleb Steele, I spent, I started WRFing in the probably early 2010s, and I was at it for a while. For the last 8 years, I was in the weather service. And so after Dr. Uccellini told me no more WRFing, so I stopped lately, but now I'm back in the private sector and now going back to grad school. So I will say, and you're going to get tired of hearing this from me, but documentation, especially like getting started, it really just ups my starts my frustration up from a level of 0. If I go into a getting started guide and it's written for Cheyenne or Derecho, because it's a lot of load this module, I can't do that on anything but that, right? So especially doing that for a public version where it's, I know you can't target everybody's system, but a pretty generalized, Ubuntu or CentOS or something install would go a long way, because once you get me started on that, I can take off, and especially with that technical note coming, because that was a little bit harder to do in the WRF when we found issues with like PBL and surface stuff in the desert. So that would like help a lot. So then the only missing link then would be just getting started, right? Because I just finally I might be probably one of the few people in the room who haven't run MPAS yet, mainly because I just got it compiled last night, because some of the documentation still says you need PIO, which is a dirty word to me. And, I discovered last night, after actually had to feed some of the errors to like ChatGPT to help me make sense of that, it was, Conda does its own thing with OpenMPI and MPISH, which you can't compile ENetCDF for MPAS while that's active. So that was a really easy thing. And I'm like, gosh, I could have done this last year. So just, the documentation to get me started quicker, I think would go a really long way.
So part of I think your frustration is that our web pages that point you to places, depending upon where you enter, you may get pointed to different places, to older stuff or older stuff that's hanging out there that we didn't realize was still reachable, and not necessarily the latest things. So we're hoping to address that with trying to have a much cleaner public-facing page that we can make sure is updated and point people to, and they'll get to the right stuff. With regards to easing builds on different systems and stuff, Michael, do you want to say anything about that? Or maybe you don't. But I think so Michael, last year he did do this regional MPAS, how easy it is to build up here, and he just sat up there with his screen and was doing things. So I think it actually is easy, but like anything, if you don't know how to do it, it looks mysterious.
And you compare it to WRF, which you've been using for decades, and yeah, it looks harder, but it really, in my view, isn't. So, but go ahead, Michael.
Yeah. Hi, everyone. I'm Michael Duda. I'm a software engineer here. So I think Caleb's point is that the online tutorial that's linked to right now for MPAS, we were lazy and we said, well, we just gave a tutorial. We wrote up about 100 pages of walkthrough for running on Derecho. We'll just link to that for now. And at some point when we get time, we'll try to generalize that. But that's a tremendous amount of work that detracts from other things. But point taken. Yeah, I think it's a matter of time writing up documentation. I think installing MPAS, if we were to lay it out cleanly, it is actually pretty easy. You need exactly 2 external libraries right now. You have to have MPI, even if you only want to run on one processor, and you need PNet CDF. That's it. So we'll move it up on our to-do list to try to write a super quick start guide, like, download mpitch 4.1, configure, make install, and so on. Like, we can promise you, you'll be up and running in under 20 minutes or something like that. 20 minutes to your first simulation. Yeah. Maybe 30 minutes.
So on that, that's not what I was up here, but I have you can actually set up an HPC environment for your, like a Linux 64 box. It's just like a AMD EPYC workstation in Conda, and have, if you don't care too much about an Intel, but just want to know G4 NetCDF, OpenMPI. And if you do that, I actually kind of reset that all up for those runs in my talk this afternoon. So all CM1, WRF, and that are all running out of that Conda environment. And for an HPC, and they're all running, OpenMPI. So I guess I need to write that up. I was just going to
contribute it to the community.
No, I will.
Yeah.
I will.
Okay, good.
All right. It's especially if you're just running on like a decent sized workstation these days. It's just too easy, because I hate setting up environments. I was going to ask you, Bill. I mean, this was from the couple of people ago. Isn't it possible to run a regional MPAS simulation one-way nested from a previous larger grid one-way regional nest?
Yes, but I think there's a trick or two you need to know. Again, I have to point to Michael. Say, Michael.
Pay attention, Michael.
Lou just asked, is it easy to run a one-way nest of MPAS?
Like, could I run
using
a 15
previous
kilometer
MPAS run?
CONUS run, and then take that as my one-way background and do boundary conditions from that?
Yeah, like offline one-way nesting. Yeah. So yeah, presuming you write out an output stream from MPAS, we have a Google Doc. We could just make it public.
Okay.
It's, what do we call that? Like, MPAS to MPAS or something. So yeah, we do have some C++ code that allows you to take MPAS output and generate lateral boundary conditions for a completely unaligned other SCVT mesh.
Yeah, I think that would be kind of useful for these people who use for WRF, at least. It's not two-way, but anyway.
Well, it covers a lot of the application space. So
I'm Wayne Angevine. I'm series at NOAA CSL. I've been doing this for a long time. I'm the primary user and supporter of the WRF single column model. There are probably other people out there who are using it that I don't know about, but if you send an email to forum or to what used to be WRF help, it usually comes to me. One of the things that would help with some of these things, I think, is if MPAS and CCPP would get closer together. And we heard something about that a couple of days ago. I didn't hear a commitment to connect MPAS and CCPP. There are things I like and dislike about CCPP. It allows you to do things you want to do. It allows you to do things you probably shouldn't do. It does at least have the advantage of emphasizing suites, which, again, my temperature has risen a bit in the course of the day today, because I don't believe that these models are modular at the level of schemes. We should not probably be swapping schemes. We should be looking at suites, or at least if we're going to swap schemes, we need to be very careful about what we're doing. But with CCPP, you can do whatever you want to do, but it does have an emphasis on schemes. It also has a really nice single column model, which has a really nice documentation. It's also actually suffered slightly from aging, but it was very, very well written when it was written, and it's a really good document. So that would help. I think people who want to use single column models should probably be considering doing that. So I guess really my question is there a commitment, or what would it take to get a commitment to connect MPAS to CCPP?
So the reason we have not done it yet is that doing it would not have gotten us access to physics we could use. Because primarily the other physics, which is in the DCC repository, a lot of it had FV3 specific code below the level of where you'd be accessing it, which was a problem. Obviously, that's going to be addressed. They're bringing MPAS in, they're going to run this physics. That'll be addressed. So that issue will be removed. And in principle, if we adopt the CCPP for our MPAS release, we should be able to pull directly from that repository, and we'll all be single source and everybody will be happy. So I think that commitment may well come soon, but part of that will be co-development of that with our partners from NOAA and the DTC. So I think that's going to happen soon.
Yeah, I Louisa again. I think we're coming at it from numerous angles, and so hopefully it will converge fairly. I'm not going to say quickly, but timely, whatever. Because the Navy is also using CCPP. We had this workshop just last fall, where one of the things was, make it more interoperable, the physics that's in the repository. So, I mean, part of the reason it ended up being more FV3 UFS specific was we needed to stand it up quickly. And that was where the funding was coming from. That was the application. So I think there's going to be a lot of work going on over the next year. We have more funding that's going into CCPP type work over the next year, specifically because we need to get ready for the MPAS transition, support that development work. So hopefully everything that's going on will stay coordinated well enough that we converge on a good solution.
Hi, I'm Hendrik. Just to add to that from the perspective of working for the Weather Service on the operational side, the more we are making the CCPP what it needs to be and not just getting there, the more easily it will be for people in operations to upgrade physics to begin with. So that is, if we want to work as a team and if we want to leverage each other's work, we would benefit from the research community also working on that at the same time. And also for what we're doing right now on operations, we deliberately run regional standalone models, one-way coupled for the HER RFS. There are arguments for doing that on the service delivery side and on the forecaster side that are on top of the model has to be good. But if we want to think forward, and if we want to think forward about potentially having MPAS becoming a part of RRFS version 2 or beyond, it would be more or less a requirement to have a standalone regional version of the model being able to run. Just as side arguments, not as another question.
Right.
So I've been pretty deep in the MPAS code for the last 2 or 3 years. And that's coming from a background of not developing models. But I think there's a few things that have helped me along the way to familiarize myself with MPAS. And I think there's a lot of discussion about the technical note, but I've actually found that there are aspects of the WRF technical note that are still applicable to MPAS, such as some of the physics stuff. And also there are a number of papers that Bill and others have written that have the equations. And I think maybe in the meantime, while they're developing that, just having a better point to some of those. Also, the tutorial slides have been really awesome that have helped me get to a point where I feel pretty comfortable with MPAS.
So the technical note is on the top of my priority list in terms of what I write. So it's coming. It's just, there's a lot to put down on paper. So does anyone else have any other comments? Because we're almost there in terms of closing this up. Does anyone want the last word before I give the very last word to Joe? Okay, Joe, it's all yours.
It's been very exciting for me anyway to see all of the active participation we've had in the discussions and so on this week. It's clear we're in such a period of transition these days, and WRF to MPAS and MPAS to CESM and UFS, that it's raised so many issues that many of you have brought up and identified, and I hope this is going to lead to some better focus in devoting our resources and priorities to identifying some of the most important issues that we face. I do want to emphasize that, as has been pointed out many times, everyone is very much resource limited. And this is intended to be, and to be successful, just must be a joint community effort in terms of development and cooperation and working together to get some of these new capabilities we're looking for. So I very much hope that this will lead to some productive direction in our work in the near future. And before we leave, there's some folks that I want to acknowledge for making this whole workshop run so smoothly. We have Kelvin Tavares, Joey Ehrman, Ryan Deltimer. I don't see them back there, but there's one. They're the folks that have been running the projection system and making everything run so smoothly between our in-person presentations and the remote ones. I've never ceased to be amazed at how smoothly this has been integrated and works so seamlessly. And so that's been very nice. In terms of administrative support, Neely Smith and Robin Ty have been so helpful. You've seen Neely out there at the registration desk and keeping everything orderly in the atrium there, which has been very helpful. Kelly Warner back there has been monitoring the remote users and relaying questions and comments as they've come up, and that's been very helpful. And finally, I want to acknowledge Wei Wang back there, even though she objects me doing it. She's led the whole planning and organizational process for this workshop and handled so many of the details that have made things run smoothly. So to all of these folks, I want to express our appreciation and give them a great hand. So with that, I guess we'll adjourn, and I hope many of you will attend the instructional sessions Friday morning.